My name is Steve Feiner. I'll be chairing the session. We have 6 papers, and I'm told we're supposed to start on time and end on time, 15 minutes total for each. So without any further ado, I will introduce the first paper by Cara Plasson, Renaud Blanche, and Laurence Niguet. I believe Laurence is going to be online and presenting. And the paper is on selection techniques for 3D extended desktop workstation with AR HMD. Thank you.
Hi everyone, my name is Laurence Niguet. I am a professor at the Université Grenoble-Alpes in France. Today, I will present a study on selection techniques for 3D extended desktop workstations with augmented reality head-mounted display. This is a joint work with 2 colleagues, Carole Plasson and Renaud Blanc. First, what do we mean by extended workstation? Our starting point is a standard workstation with a physical display, a keyboard, and a mouse. And we extend the standard workstation with virtual views displayed on an augmented reality head-mounted display. So here the user can see the 2D map on the physical monitor and a 3D point cloud displayed on the head-mounted display. Extended workstations offer 2 key benefits. The display space is unlimited and fully adaptable. The second advantage is the possibility of stereoscopic 3D views for 3D visualization. In our study, we consider 2D views displayed on the physical monitor and 3D views displayed on the augmented reality head-mounted display. But what about interaction with such an extended workstation? Without adding input devices such as 3D mice, we have the keyboard and mouse, as well as mid-air interaction. But with mid-air interaction, for a selection task, the users touch the object of interest directly with their finger. This interaction is simple and direct, but also inaccurate and tiring. So for an extensive use, mid-air interaction is maybe not appropriate. To avoid the problems of mid-air interaction, we focus on mouse-based interaction. On the physical monitor, the technique is well known. In our study, we explore how to use the mouse when interacting with the 3D views, and also in which cases it will be interesting to use a mouse instead of mid-air interaction. For example, we can suppose that for selecting large targets, mid-air interaction is better because it's direct and easy. But for smaller targets, using the mouse could be useful. In addition, the change of interaction between mouse and mid-air can have a cost. So we explore solutions for mouse-based selection techniques that implement the metaphor of the image plane selection that is consistent with a desktop mouse control. Indeed, our goal is to define a continuous interaction space. We identified 2 dimensions that structure the design space that we explore. The first dimension defines the interaction techniques. When using a mouse, the cursor can move either on a vertical plane, in the same way as on a physical screen, or on a horizontal plane. The second dimension considers the relative position of the 2 views. Do we place them next to each other or below? We obtain 4 mouse-based techniques. Finally, since we want to compare mouse interaction and mid-air interaction, we add a third technique, the direct touch interaction. Overall, the design space includes 6 techniques that we implemented in a simple system. The system displays a 2D histogram on the physical screen and a 3D view, a set of 3D spheres, on a headset. The 2 views are tightly coupled. When the user selects a bar in the histogram, the system displays a red sphere in the 3D scene. Using this system, I present the implemented interaction techniques identified in our design space. First, for mouse-based interaction techniques, with a cursor moving on a vertical plane. The 3D scene is placed behind a virtual vertical plane similar to a screen. It is a metaphor of the double screen. The cursor moves on this vertical plane. A ray perpendicular to the plane is attached to the cursor to select objects. The mouse wheel is then used to adjust the selection depth if several objects are intersected by the ray. This plane is placed either to the right or below the physical monitor. When it is placed to the right, the cursor comes out of the right side of the physical monitor and enters the virtual plane by its left side. The transitions are very similar to the transitions done with two physical screens. The current selected 3D sphere is displayed in yellow if it's not the target and in green when it is the target. And the user validates the selection by pressing the left mouse button. When the plane is placed below, the cursor comes out of the bottom side of the physical monitor and enters the virtual plane by its top side. And the technique is similar to the previous one. Now for mouse-based interaction, but with a cursor moving on a horizontal plane. The virtual 3D scene is placed above a virtual horizontal plane, and the cursor moves on this horizontal plane. The same ray as in the previous techniques is attached to the cursor. This plane is placed either to the right or below the physical monitor. When it is placed to the right, when the cursor emerges out of the bottom right side of the physical screen, it enters the virtual plane by its front left side. When the plane is placed below, the plane lies directly on the table. And we see here that the transitions between the physical monitor and the virtual plane are visually continuous as opposed to the previous technique. Finally, for mid-air interaction, to select a sphere, the user touches it with its fingertip. The validation of the selection is done by pressing the space bar. As before, the virtual scene is placed either to the right of the physical monitor or on the table. The user selects the bar of the histogram using the mouse and then switches from the mouse to mid-air interaction to select a virtual sphere. A hand mesh is displayed and a disk following the user's index fingertip is displayed for precision. The technique is similar when the plane is on the table. Having presented the 6 interaction techniques that we implemented, I now explain the steps that we follow to experimentally explore the design space. We followed a 3-step process and we conducted 3 studies. For the first 2 studies, we used a system I presented with a 2D histogram display on the physical monitor and a set of 3D spheres on the headset. We conducted a first study to evaluate the usability of the techniques and a second study to evaluate their performance. We then wanted to confirm the key insight from these studies in a more ecological context. To do this, we perform a task-driven study. We implemented a second system. The system displays a 2D map of the world on the physical monitor and a 3D scatter plot on the headset. We use a Gapminder world dataset. The scatter plot shows the number of babies per woman, income and life expectancy in the world. Each sphere represents a country and its diameter is proportional to the population of the country. The 2 views are coupled. When a user selects one or several regions of the world on the 2D map, the scatter plot is updated. The user can also select a 3D sphere to obtain information about the corresponding country. The information is then displayed at the bottom left of the virtual plane. Using this system, we ask participants to perform exploratory tasks. For example, which country in Asia has a life expectancy of 40 years? We asked 14 participants to perform 15 exploratory tasks, and we concluded the study by a questionnaire about the usage of the system. Based on the previous studies, we implemented 4 techniques. The participants have the choice of the techniques at any time. Let's see them in action. First, the user can rotate the 3D scene by using a virtual slider. The user can position the 3D scene on the right side of the physical monitor or below the monitor. And at any time, both mouse and midair can be used to select a sphere when the 3D scene is placed below or on the right side of the monitor. What are the key insights from this study? With this study, we confirm in a more ecological context, the 2 key results from our first 2 studies. First, mouse and midair interactions are useful and the position of the 3D scene should be flexible. Another key result is that the mouse interaction is efficient, easy to use, and well liked by participants. To conclude this study on selection techniques, we provide 2 main guidelines for the design of extended workstation. First, mouse interaction is efficient and well liked by users. This is also important to lower entry barriers for the adoption of immersive technologies. There is a need for there is a need for flexibility to allow the user to position the 3D scene everywhere, as well as to choose mouse or midair interaction. For more information about our experimental studies, please see our paper. Thank you for your attention.
Thank you, Laurence. Do we have anyone who wants to ask a question? Come on, raise your hand. No one at all? Okay, in that case, I have a question. So what you've done basically has a volume, a rather small one, that's situated at a particular place relative to the monitor. And have you thought about, given that it is a head-worn display and it's tracked, being able to have a lot more data that's surrounding that physical monitor? And what techniques you might use, building on what you've done, to handle that?
Thank you for the question. We didn't consider a very large volume, and we only consider one virtual screen right now. But we are starting to explore another domain, which is visualizing a trajectory in a city, and we will have multiple views around the physical monitor. And we plan first to really focus on mouse-based interaction. We don't want to add new devices, and we would like to see something that will be used every day by users, you know. So we plan the long-term studies with real users for a system studying trajectories in a city, daily mobility data. That's our goal. And one promising avenue we have is to study the combined usage of midair and mouse, because we observe in the experiments that we have done that the user were using both at the same time. So we are going to multimodal interaction.
Okay, thank you. So I think we have time for one very fast question. Bruce?
Bruce Thomas, University of South Australia. I was wondering if you're going to incorporate like some known techniques for resolving occlusion, because some of the spaces that you have quite dense sets of objects, and you have basically a single point for defining that. Have you thought which occlusion resolving techniques you might use?
Could you be more precise about how to resolve occlusion? What do you mean? Because right now we can select an object behind by controlling the depth of the cursor. So and we can rotate the 3D view. So what do you mean by occlusion?
It's sometimes difficult to precisely select something, and there might be a mistake between multiple spheres that are very close to each other.
In the second experiment that we conducted, we control the density of the space, and we have quite a very precise selection with the mouse. So what we observe is that the user was using the mouse when you need to be very precise, and we have very small target, and we control the size of the target, and we control the density of the space. So I believe that with the mouse, we can be very precise when you want to select one point.
Okay, thank you.
Okay, thank you very much. Okay, let's have a round of applause for the speaker.
Thank you.
Our next paper is also going to be online. I'm not sure who's going to be presenting it. And it's by Yuan Li, Ibrahim Asadullah Tamid, Fei Liu, and Doug Bowman. And it is entitled Evaluation of Pointing Ray Techniques for Distant Object Referencing and Model-Free Outdoor Collaborative Augmented Reality.
Thank you, everyone. Today, I'll be presenting our paper on the evaluation of pointing ray techniques for distant object referencing in model-free outdoor collaborative AR. My name is Ibrahim, and I worked on this project with my colleagues, Dr. Yuan Li, Fei Liu, Dr. Doug Bowman. Before diving into the details, let us give some background first. So first and foremost, it is believed that awareness is important in collaborative tasks. To be more specific, joint attention of an object of mutual interest is a common requirement for many collaborative tasks. One example could be two surveyors trying to come in agreement about the location of a distant object when they themselves are spatially separated. Another example could be like two coaches trying to plan the possible course of action of a player when they are spatially separated and when they have to point towards a specific location on the field. Typically, when the two collaborators are close together, this task is fairly simple. They could just point at a target and confirm via verbal communication. But things could be much harder when there are larger distances between the collaborators. So the question becomes, how can we facilitate the communication about object location with 3D interaction techniques when we don't have any knowledge of the environment prior? So laser pointer is a very commonly used tool to overcome this limited communication. Let's say when two users are close together, they are talking about a closer target, laser pointer can help identify the target with precision because it's bright and it's easy to follow. The effectiveness of laser pointer can be affected by, let's say, lighting condition. If the light is too bright, the ray could be almost invisible, but the observer could still do a visual search of the targets and could come to a conclusion about the target by observing the intersection point with the laser with the real world. Now, what happens if the participants are further away from each other? Then even the laser pointer can't help much because the intersection point could be too tiny to spot. With ideal air that has access to an environment model, we can use a virtual ray that intersects with the target location, leaving visual highlights of the target to help the observer understand about the reference. But the real world is dynamic, and it's not always possible to get an environment model. That's why we need model-free AR. In model-free AR, the challenge is that the ray cannot properly occlude or intersect the real world. It kind of extends, which might make it a little ambiguous for the observer, and they might not have a full understanding of the reference that the pointer is trying to make. In one of our previous study, we actually identified two ambiguities for this naive gaze ray. First one is visual ambiguity, where the ray appears to visually cross like multiple objects at the same time. And the second one is spatial ambiguity, where the user cannot perceive the orientation of the ray when the target itself is surrounded by multiple targets at the same time. Now, as you can see, the visual ambiguity occurs when a single ray visually crosses multiple objects. We designed a double ray technique to overcome this. The idea is that a distant object, a distant collaborator, or the pointer is asked to cast two rays pointing at two distinct geometrical features of the target. Typically, that's the top and the bottom of the target. So the observer has a better idea about the target's location. The insight is that by increasing the number of rays aiming at different parts of the target, the visual matching condition is more strict for the observer. So instead of just looking for a single ray that passes through the target, the user can look for objects that are kind of bracketed by two targets. Secondly, we developed the parallel burst techniques to overcome the spatial ambiguity condition. To do so, we first create a virtual segment that is kind of parallel to the actual ray. We also identified the location of the ray and find the perpendicular ray that is perfectly perpendicular to the virtual ray, and we draw some parallel bursts in front of the observer. The observer could also see the closest point on the ray. The idea is that by observing the direction of the perpendicular ray and the number of bursts in front of it, the observer may have a better understanding of the ray's position and the direction. The advantage of the technique, this technique, is that the observer has more information about the target. The disadvantage is also that he has more information, so it may be harder to interpret, and the observer may have to go through a learning curve to understand. We performed an experiment, in a previous experiment, where we ran AR simulation study in VR to evaluate these two techniques. We implemented the scene in VR with a giant chessboard to add depth perception. We had 6 red spheres as targets, and a virtual collaborator worked as the pointer who could aim a perfectly accurate ray every time. The user's task was to find the target using these two techniques. What we found out is that typically the observers were more accurate with the double ray technique, but the observer were slower with the parallel burst. However, it is kind of unclear how well these results would translate to a real-world AR system. First, while the AR simulation is a very common approach to conduct controlled and repeatable user experiments, this approach may fail to replicate these results in AR, especially when we're talking about real-world experiments. Moreover, we also consider the role of the observer, so who always, and the pointer was identified with virtual collaborator who was always too perfect. So we don't know that how much a real human pointer would perform and how that affect the technique's performances. These were never investigated. So we investigate this in our current experiment. We designed a new study with modification to both of these techniques. We also designed a pointing interface for the pointer. We designed the study in a large model-free real-world environment. It was basically a site on our campus with 7 actual lampposts as targets. We had 32 participants, that's 16 pairs of observer and pointer. And for each technique, the participant took turns being an observer and a pointer to identify the target lampposts. We used image refinement technique to mark the lampposts with virtual spheres for better visibility. And both the observer and the pointer were identified with virtual avatars, also for better visibility. And this is what it looked like from pointer's perspective. This is where the pointer is trying to identify a target with single ray. And onset draws the ray. The observer is trying to find the target, reference of the target with single ray and parallel burr. For our experiment, we had two independent variables, number of rays and orientation cues. That gave us 4 conditions. So single ray with burr, double ray with burr. For independent variables, we have the observer accuracy and time. We also used a modified system usability scale questionnaire for the observer, and we used a NASA TLS questionnaire for the pointer. We had these 4 risk questions. The first 2 seeks to understand the effectiveness of the 2 techniques, double ray and parallel bursts, on model-free collaborative AR. The third one seeks to understand the significant decrement on the pointer when they are using the double ray technique. And the last one seeks to understand the trade-offs the pointer needs to make the collaborative experience more effective for the observer. And here are the results. Regarding research question 1, we had a hypothesis that the double ray technique will have significantly better performance overall. As seen from the left image, we see that the double ray technique indeed had better observer accuracy, but it also took more time, as seen from the right image. But that extra time was not an issue for 97% of the participants who preferred the double ray technique over single ray. Our second question was about the effectiveness of parallel bursts. We hypothesized that the observers will be more accurate with the parallel bursts, but slower. That was not supported. We found out that the parallel bursts did not help with the accuracy, but they indeed significantly slowed down the observer. However, still, most users preferred parallel burr, especially when the only other information available was single ray. So 87% preferred single ray with parallel bursts over just single ray. And for double ray case, it was 59%. As for our fourth question, our analysis revealed that, as seen from this graph here, the greater the pointing error, the lower the observer accuracy. We have seen from the previous questions that the double ray technique leads to greater observer accuracy, but it also has higher pointing error. But it was still having higher accuracy. So that means that the observers had sort of a tolerance towards the error made with double ray. So that supports our hypothesis that the extra cost in usability by the pointer will ultimately pay off in increased performance by the observer. Overall, the takeaways from our study is that for distant object referencing task, our technique double ray contributed to a better observer usability. Even though it was costly for the pointer, it ultimately paid off in the object referencing context when two collaborators were working together. Secondly, our participants preferred the parallel bursts, even though it did not help with the observer performance much. We can see that these findings aligns with the findings from our previous simulated study. We also got some additional insights from this study, such as the trade-offs the pointer and the observer needs to make to facilitate an effective collaboration in real-world AR scenario. Now, there are 2 ways that the future studies could go. First, we could look for other artificial spatial cues in distant object referencing. Second, major challenge in this work was to find the trade-offs and understand it between the observer and the pointer. So it would be nice to have a method for calculating a collaborative usability score for such techniques. It would help the designers to make important decisions when they're designing collaborative systems in this area. With that, I conclude my presentations. Thank you, everyone.
Thank you. So I think we have 3 minutes for questions. Hands, please.
Thank you.
Hello, Mark Satkowski, Interactive Media Lab Dresden. Thank you for this nice talk. I have a question which wasn't so clear in the presentation, I guess. Were the observer and the pointer able to move in the scene, or were they always fixed at the position?
That's a good question. So the observer and the pointer were always at a fixed position. They were about 70 meters apart from each other. So their positions were fixed. Also, the positions of the lampposts were fixed. We decided about the position in such a way that they could not verbally communicate with each other. They would just have to depend on the rays alone.
Okay, and then maybe a short follow-up question. So would it be more normal for people to, if things are really far away, to get closer to it, to make it easier for us to point it in the first place? And maybe even if is it so normal to point to something that is behind something else? So the occlusion of real-world objects would be of hindrance if I want to point to something?
Do you mean it would be easier for the collaborators to be closer?
Yes, but or more or less, if something is farther away, maybe I get closer to it because it's easier for me now to point to it. Wouldn't it be more normal? And how would your results change in that regard if they could move closer?
That would be normal, but there are like use cases, for example, that they discussed during the first half of the presentation, where the collaborators have to be in a distant way, so that they can have like different perspectives of the environment from different areas. So that way they have to be distant, but they also have to talk about a common distant location of distant object. So that's where we think this pointing techniques could help.
Okay, thank you.
Thank you.
Thank you very much. Let's give the speaker a hand.
Thank you.
Okay. And our next presentation is also going to be done in person, being presented by Katja Krug. And it's called ClearSight, Exploring the Potential of Interacting with Transparent Tablets and Augmented Reality.
Hello everyone, my name is Katja Krug, and today I'm going to present our work ClearSight, exploring the potential of interacting with transparent tablets in augmented reality. This is joint work with my colleagues Wolfgang Büschel and Konstantin Klamka and Raimund Daxelt at the Interactive Media Lab Dresden at the Technische Universität Dresden. So, additional mobile devices can be used to support HMD-based augmented reality. They serve as input devices for touch and tangible input, but they can also be used for additional output. However, they lead to occlusion, both of the virtual scene and the real-world objects. To address this, we introduce ClearSight, a research platform based on a tracked, touch-enabled transparent panel that can be used to support interaction in AR and serve as a testbed for transparent mobile devices. In our research, we built on prior work in mobile-assisted AR and interaction with transparent devices. For example, tablets and phones have been used both as general tools and for specific usage contexts, such as the exploration of medical data. They're also used as controllers for immersive analytic scenarios, and often combine touch and spatial input. They also serve as tangible magic lenses, and of course, there's also ample research on the general topic of mobile devices in AR, where the device itself is the primary input and also output device. In earlier work, transparent devices serve as tool glasses on tabletops or to augment documents. Also, there's been research on larger form factors, as seen, for example, in digital signage applications. And while there is some prior work on transparent handhelds, In mixed reality, there is little research on this combination and no really in-depth analysis for this specific form factor. So, with our paper, we want to make the following research contributions. Based on our analysis of the related work, we contribute the concepts of combining HMD-based augmented reality with a transparent tablet. We developed an open research platform and a prototype, and based on this platform, we implemented 3 different use cases to examine the advantages and challenges of this setup. And then we used our prototype to collect expert feedback in a number of hands-on sessions and derived qualitative insights. So our general concept is as follows. We have a touch-enabled transparent device which provides input capabilities such as touch or pen, and also spatial input. The device is the device is tracked by an external tracking system, and it is used in combination with an AR HMD, such as the HoloLens. And the AR headset provides the rendering capabilities for the tablet and simulates a transparent display. For our prototype, we constructed a custom-built transparent handheld tablet consisting of a Raspberry Pi 02W, a 10-inch capacitive multi-touch surface, and a battery shield. We attached infrared tracking markers to the frame and used an OptiTrack infrared tracking system to locate the tablet. We also combined infrared and QR code tracking targets in the scene to allow us to unify the tracking space of the tablet and the HoloLens. The touch that is received on the tablet is transmitted to our Unity application wirelessly over the network, and we include remote rendering for both the general augmented reality content and simulated on-surface rendering. If you're interested, our building instructions, a part list, and also our code are all available on our project page. To further explore our concept of a transparent input panel, we built our interaction and visualization concepts on 2 further components, working together with the transparency of our surface. The tangibility of the panel and its usage as an AR prop, and the possibility for pen and touch input on its surface. These 3 aspects are the pillars of our tangible, transparent, interactive window and form the foundation for our interaction and visualization concepts, with our individual concepts being based on either 1 or a combination of 2 or 3 of these aspects. So our interaction and visualization concepts can be separated into 3 main categories. First off, we have data manipulation and exploration, which consists of selection and manipulation and 3D volume data slicing. Further, we envision the tablet to be used as a frame of reference for menus and UI tools, including conventional touch menus and also further adapted UI tools and widgets. And lastly, we created interaction and visualization concepts for sketching and annotating in 2D and in 3D, which I want to show you quickly a little example of. Our tablet or annotations are separated into 3 main categories, which is first on-tablet annotations that can be released into 3D space, as you can see. In C2 annotations that can be directly drawn into 3D space. And lastly, projected annotations, which enable the user to remotely draw on surfaces from their correct viewing perspective. So based on our interaction concepts, we designed and implemented 3 distinct use cases where we thought that they might benefit from the usage of our transparent interaction panel, which would be volume data exploration, the control of smart home applications, and collaborative data analysis. The first use case revolves around the immersive exploration of volume data. In our implementation, we use MRI data. And here the transparent panel can be used as an interactive window to scale the volume and to rotate it. It can also be used as a tangible prop, as you can see, to pick it up and relocate it or further inspect it. The data can be clipped with a panel. And also it's possible to attach alternative data representations, such as this CT scan, onto the panel to get further insight. The clip data can also be frozen in its current state for further inspection or maybe annotation. And the user can create bookmarks in the volume data to indicate a desired position of the panel. And of course, the volume can generally be annotated. Our second use case takes place in a smart home environment and revolves around the control of smart home applications and appliances. The smart devices can be observed and selected through the panel, as you can see, and the user can adjust the parameters using the UI elements, such as changing the color of the light. And also what you've just seen was you're able to connect the smart devices to draw logical connections between them in a way to link their functionality. Our third use case revolves around the collaborative analysis of abstract data and data physicalizations. And the panel can be used to filter crowded visualizations, such as scatter plots, or virtually annotate physical paper and interact with virtually enhanced physical documents and objects. To validate our concepts and use cases, we conducted 5 different review sessions with experts in the field of augmented reality. Each session lasted around 90 minutes, and participants were encouraged to think aloud during the process. The participants went through all of the 3 implemented use cases and could freely explore all of the implemented features. And we mainly used these review sessions to gather some initial insights into how our general concept is received, and also some early feedback for our interaction visualization concepts and maybe the use cases. So through these expert reviews, we were able to gather some initial feedback, which was overall quite positive. In general, the transparency aspect of our concept was well received, especially when the scene included physical objects, like in the smart home use case. The participants also overall expressed their liking for tasks that involve window interaction, which was noted to feel natural and intuitive, and also for spatially tracked surface input, specifically in situ annotations and projected annotations. And the participants also tended to agree with our initial theory that our transparent tablet could have the potential to facilitate collaboration. However, we need to conduct more research into this to verify this claim. On the flip side, most participants experienced some form of perceptual difficulties during the window interaction because of the binocular parallax, of course, that users experience when they interact with 2 different focus planes. And here it would be necessary to minimize the amount of focus switches during interaction. And perceptual difficulties were also experienced during spatially tracked surface input, such as in situ annotations, because of the depth ambiguity of 2D strokes in 3D space. And here the users would like to have some kind of depth cue or depth indication, such as shadows, for example. So with our research platform, we provide the technical foundation to further explore the issues that I've just mentioned, and also, of course, their solutions, and also a platform to further extend or build onto our interaction visualization concepts and extend our use cases. And in general, just explore the potential of transparent interaction panels, not only in AR, but also just removed from the AR context. With this, we also provide an easily replicable rapid prototyping tool for future transparent displays. Okay, for more in-depth information regarding our findings, our concepts, our use cases, whatever, please refer to our paper and visit our project site, imld.de/clearsite. Thank you very much for your attention.
Good. Do we have any questions?
Soyoung from KAIS. Thank you for your presentation. I found it very interesting. What would be the benefit over the using standard tablets in video see-through mode? Like, cameras on the standard tablets versus your work?
What the main difference is?
Main difference and what would be the main benefit over it?
Okay. In comparison to video see-through, tablet, AR, the benefit, of course, is perspective. If you take your tablet and you tilt it some way, and then the camera aims at the floor, then you lose your viewing perspective, and this needs to be corrected, which is also a bit difficult, of course. So this is something that can be removed entirely. And also, in general, of course, as I just said, like the tablet isn't only meant to be seen as like an AR prop, but also as a way to simulate actual transparent tablets. So the goal would be in the end to say we can leave the headset out completely and have the UI elements actually displayed on the transparent display, which would then just be like a bit more straightforward than actual video see-through.
For another question?
Thank you very much. Do you consider different size tablets? Because I could almost imagine having something that's like a clear whiteboard that you roll around, and then it's a nice big collaboration surface that you can work on. I guess the question is, why did you pick the size you picked, and do you see any issues with changing that size?
We mainly focused on this specific size because research into bigger, like stationary transparent tablets is already a bit further and a bit more, there's a bit less to explore. This is, I think, one of the points why we like to pick a mobile one. And second, because of the mobility, because all of the spatial input that can be created with a mobile tablet, as you have seen, for example, the slicing, picking up, scooping, as well, these kinds of motions. So we really wanted to see that we have all the benefits that additional mobile devices bring into AR, and just take them up, use them, and have an additional benefit of transparency added to it.
Okay, time for one more question. A quick one, please.
Thank you for the very interesting talk. I think I have missed your explanation, but where is the ray originated from? Is it the dominant eye or the midpoint of two eyes?
It is originated from the camera of the HoloLens, so I think that lies like in the middle and like a little bit upward. So it's of course not perfect because we have this parallax effect. Yeah.
What is the general feedback of users about the misalignment?
I'm sorry?
Misalignment.
Yeah, misalignment.
Yeah. So if the dominant eye is actually dominating what you're seeing, you know, that ray should be originated from it. So I would just, you know, if you're seeing the visualization with two eyes,
yeah,
then you will still always have some misalignment.
Yes, of course. This is also something, I think you were talking about the issue with like further away and trying to focus on like a closer plane. Yeah, this is still an issue and needs to be corrected. There are also, maybe before we correct this issue, that we could also include additional techniques that kind of help support it. For example, to offer like a gradient stationary way to create projected annotations, for example, to first create them on the tablet so you have it perfectly aligned with your finger, and then you can push them out into the world and have them like on a whiteboard or whatever to kind of circumvent this issue.
Okay, thank you very much. Another hand for the speaker, please. Okay, so we move back into virtual space for our next paper, being presented by Xiaolong Yu, entitled Distant Object Manipulation with Adaptive Gains in Virtual Reality.
Hello, everyone. I'm Xiaolong Liu from Beihao University, Beijing, China. Our paper is distant object manipulation with adaptive gaze in virtual reality. This work is together with Lily Wang, Shuai Huaishi, Xina Liu from Beihao University. Object manipulation is one of the most basic operations in VR applications. The efficiency and accuracy of the manipulation directly affect the effectiveness of the applications. However, when the object is far away from the user, how to efficiently and accurately manipulate the distance object to the target. There are some related works focused on how to improve the accuracy and efficiency of object manipulations. Now, existing methods mainly adopt two ideas. The first idea is to manipulate the objects through the multiple manipulation points. In the left video, Glamour introduced the pinwheel technology, which uses pins to constrain the rotation of objects to improve the efficiency and accuracy of manipulation. The second idea is to use the mapping between the physical motion of the user's head and virtual objects to improve the accuracy and efficiency. In the right video, Kim proves the non-line mapping method to improve the efficiency of the manipulation. It determines the dynamic gaze through the speed and acceleration of translation and rotation of the head. Manipulation gaze are defined as some adjustment factors that map the head control motion to the motion of the manipulated object. Manipulation gaze include three parts: translation gaze, rotation gaze, and scale gaze. However, the previous method didn't consider the imprecise perception of the user's head movement speed, so the efficiency and accuracy still need to be improved. The challenge is how to determine the manipulation gaze GT, GR, GS per frame adaptively. In this paper, first we determine the maximum and minimum of manipulation gaze. Then we find the wheel-dependent fitting functions for gaze. At last, we evaluate manipulation gaze fitting functions. In first step, we design an experiment to obtain the maximum and minimum manipulation gaze that the user can accept. In the task for maximum gaze, the user is required to roughly manipulate the object to the target position with a given gaze. The initial translation gaze is 150.5. Through visual feedback, if the user feels that the motion of the object is too large relative to the movement of his head, he presses the smaller button on the handle, and then the object is set to the original position. And the system uses the dichotomy method to generate a smaller gaze, and vice versa. The user manipulates the object and gaze using the newly generated gaze and repeats the above process until he feels that the motion of the object is consistent with the magnitude of the motion of his head. On the contrary, the user has to press the large button on the handle, and then the object is set to the original position, and the system uses the dichotomy method to generate a larger gaze. The user manipulates the object gaze using the newly generated gaze and repeats the above process until he feels that the motion of the object is consistent with the magnitude of the motion of his head. For minimum gaze, the task is to ask user to finally manipulate the object to the target location in a similar process to the above. The figure shows the scattered plots of the maximum and minimum values of manipulation gaze collected through the above experiment. These are maximum and minimum translation gains. These are the maximum and minimum rotation gains. Those are maximum and minimum scale gains. In the second step, first we generate two auxiliary views based on the user's current viewpoint. One is the top view of the object, the other is the left side view of the object. According to these views, three object target metrics are calculated to measure the relationship between the manipulated object and the target, the projected area portion, the distance, the angle difference between the manipulated object and the target at the current viewpoint and its corresponding auxiliary viewpoints. Then, we design an experiment to explore the relationship between the visual metric and the manipulation gains. The task is to ask the user to adjust the gain during the manipulation multiple times until he feels the most appropriate gain. If the user thinks the current gains are small or large, he presses the reset button to put the object back to the set sentence, increase or decrease gains, and then manipulate the object to the target. This process is repeated until the user thinks the current gains are appropriate. The user presses the reset button and then presses the save button to save the current gains and the object target matrix corresponding to this gains. Based on this collected data, we derive the three fitting functions for visual metric and translation gain, rotation gain, and scale gain. In the evaluation step, we record 6 new participants repeated the experiment and collected the same data. We quantify the error A and the error rate ER of the fitting function by comparing the manipulation gains chosen by the participants. As shown in this figure, the errors are very small, and the ER rotation, ER of translation gain is 5%. Rotation gain is 6.7%, and the scale gain is 8.6%. We designed a study with 3 tasks to evaluate our method. There are 4 control conditions and an experimental condition with our method: AC, CC1, CC2, CC3, and CC4. Our method was designed to allow the user to manipulate an object to the target efficiently. Thus, we formulate the following hypotheses: H1, H2, H3, and H4. We designed experiments with 3 cases to manipulate the cube, body, and engine to the target. Task performance was measured with the following objective metric: computation time, expedition error, rotation error, and scale error. This table shows that AC had the significantly less computation time, position error, rotation error, and scale error in 3 tasks. We also evaluate the task load and the usability of our method. Compared with all control conditions, the task load of AC is reduced significantly. Compared with all control conditions, the usability score of AC is increased significantly. In conclusion, we have proposed a distant object manipulation method based on the adaptive gaze in VR to improve the efficiency and the accuracy of manipulation. Our method improves the efficiency and accuracy of VR object manipulation. Our method makes the task load smaller and outperforms the others in usability. There are some limitations of our method. The first limitation is that the gain may vary significantly when the user will charge little or no charge, while the secondary will vary greatly, which makes user feel inconsistent. The second limitation is that we only consider the gain calculation method when the user is standing in a relatively fixed position to manipulation the object. The last limitation is that our method now doesn't work for cases with unknown targets since we use the information of the target to compute the case. There are some future work. One future work is to remove auxiliary views at some manipulation points to improve the intuitiveness and naturalness of manipulation. Another possible future work is to have prediction step that tries to identify the most likely target in the scale and also captures the user's gaze at the target area. Another possible future work is to investigate the distant object manipulation accuracy when users complete manipulation tasks with different durations. That's all. Thank you for your attention.
Okay, thank you very much, Xiaolong.
Yeah, thank you.
We have some time for questions. Come on. Gonna make me do it? Okay. Great talk, Xiaolong. Out of curiosity, have you thought a bit about moving targets? Because you're basically trying to go and copy the position and orientation and scale of a static target. What if the target itself was actually moving? Have you thought about how your techniques could be used for that?
Thank you very much for your question. Your method, the relationship between the target and the manipulated object is measured at a functional relationship between the metric and the manipulation gain is established. And the target is our future work. We think we can get a prediction step, for example, identifying the most likely target in the scale or capturing the user's gaze in the target area. And we have proposed the solution to solve the problem in the future. Okay, I hope this also will. I hope this will answer your question. Thank you.
Yes, thank you.
Yeah.
Anyone else want to ask a question? Okay, in that case, thank you very much, Xiaolong.
Thank you.
And we are now going back into real life space, but first I'm reminded we should indeed give another round of applause. So our next paper is going to be given by Mina Destan and Michelle Ferrantino, and it's entitled Gestalt-Driven Augmented Collimator Widget for Precise 5 Degree of Freedom Dental Drill Positioning in 3D Space.
Okay. Thank you, everybody. Thank you, Chair, for the presentation. I'm Michele Fiorentino, and together with Mina Dastan, both from Polytechnic University of Bari, we will present this research. And this topic, our research addresses minimal invasive dental implantology. I don't see the laser here. Can I have the laser, please? Laser pointer. Yeah. And thank you. Okay, so as you can see from the picture here, this is a growing healthcare industry. It's a kind of $4 billion industry, and also growing. Basically uses 3D tomography in preoperative, and later mental insert to be fixed in the patient bone. Exactly, this is the insert. As you can see, this insert should have a very precise positioning. In fact, although it provides a lot of medical advantages, it is very challenging for the doctor, as it requires high precision of spatial and angular positioning in 5 degrees of freedom. 5 degrees because the rotation around the tool is not influenced. Instead, the error can have very severe damages to the patient, like constant pain, basically. So the current approaches to drill positioning problem are both not optimal. Hardware surgical guides are expensive. So basically, there are these guides, which are hardware. You can barely see it's transparent. And they are 3D printed and then applied. You need a lot of them, and they are disposable. So it takes a lot of time to build it up and then pollute. The other approach is 2D monitors on the operating theater that requires the dentist spatial mapping and divided attention. So basically, you have just a monitor in the operating theater. For this reason, we want to explore the use of augmented reality for 5 degree of freedom positioning from a visual interface standpoint. So we don't want to bother about tracking. So there are other people doing research on this. We start with the systematic review. We will propose a novel innovative widget and then compare to the golden standard. Yes, we performed the systematic review, and we found that there are some similar solutions. Exist some widgets for the specific task, but they are limited to a quasi-static approach. The common approach requires the alignment of 2 cylinders. So you can see the 2 cylinders. One is in the planned target, and the other is on the tool. Our goal is to improve this design. For doing this, we inspire by real-life tools, like high precisioning focus in photography. Some of you never know this technique, but in the past, photographers manually focus. And also other engineering tools that I will show later. We found some common aspects in this design. They are analogic, interactive, and provide visual feedback. We discover that these tools have a common point together, the use of the Gestalt principles. The Gestalt theory is inspired by the German psychologist that Gestalt means unified configuration of forms or shapes, and is defined as a set of principles predicting human visual perception. In particular, we are interested to reification, that is find patterns in quick and pre-attentive way. So basically, our brain, without processing, mental cognitive processing, automatically find this square, which is actually not drawn in the picture, but we find it easily. So we want to leverage this principle in our design. In reflex photography, I want to start the video, because maybe some of you never saw this in reflex. It's starting. Yes. Split prism is an optical tool that displays image divided in 2. As you can see, the bottom half is separated by the top half. By focusing manually, the user can have a perfect image, so sharp, razor sharp image, just to find the alignment between the 2 sharp images on the bottom and the top. Some of you used this. And this is an inspiration for our tool. Another inspiration is the caliper. I'm a mechanical engineer, so I learned how to use it. And a caliper, what does in particular? Apart reification of finding the collimation of lines, which is basically like every tool, caliper has the nonion, which is an amplification of the error by a scale. This bottom scale is amplified, so a little bit larger or smaller. Basically, by aligning the two scales, I cannot teach now, but there are a lot of videos on YouTube, you can reach a precision of fraction of millimeters, so one cent of millimeter, when basically our normal measurement without that is 1 millimeter. So with that tool, we become 100 more precise. So there is a video, but I go on. Yes. So our tool we called augmented collimator widget is designed for be using in an augmented reality for the specific application, and presents 4 key points of innovation that we will present now. And as you can see here, it's not easy without explain how it works, but when you know it, it's easy to use. So the first thing we did is component separation. So the spatial problem, the 5 degrees of freedom, is separated in 5 sub-widgets, one indicating the error in one component. And they are differentiated by the triangles for the positioning widget and the circle, half circle for the angles, the 2 angles we have to control. So basically, collimation is clearly spotted by the reification. So your brain quickly see the X here and the circle shape. Another aspect is amplifications. Amplification of each component is applied by a piecewise functions, starting from the accepted error. So this is we are not interested because we are here, we reach the target. We have a linear function, a linear gain, and then clamped to avoid the widget to go out of the visuals. So when the widget is, when the error is, we see the scale of error, and here the widget visualization. So it's amplified till a maximum. And another aspect is that we arrange the 5 widgets in a special way in order to improve the visualization. So you can see here these are the 3 components for spatial and the 2 components for angles. And well, we noticed from the first experiment that preliminary tests show visual clutter. So we implemented a dynamic hiding function of the collimated components. In particular, the user will see disappearing those collimators one by one till you get the result. So basically, when you don't see nothing, means that you are in the precision level. I can pass to you. Thanks.
Thank you. So in the experiment design, we state main 5 hypotheses to compare both widgets, and we look for if our widget has more positional or angular accuracy and better perceived performance, and eventually less execution time and mental load. So we did a within a subject experiment in AR simulation and VR between 30 voluntary students to compare both widgets. In the setup, we provided our volunteers with Oculus Quest 2 and dominant hand controller, the trigger button for the confirming tool positioning, and the Greek button was for the grabbing the drill tool. They must sit on the stool chair and were not allowed to use no arm support in order to simulate the real dentist condition. So both widgets is implemented in Unity 3D as a prefab, and they were visually equivalent to an HoloLens 2 displays. And the experiments were set up in 2 treatments, let's say, and in the training, they were in the empty room with 32 implant targets, 30 centimeter radius around the initial tool positioning. And in the test, they were in the dental room simulation with 32 targets, 16 for the maxilla and 16 for the mandibular. So the application automatically saved the positional error in millimeter and angular error in degrees. and also the task time was saved for between the target displays and button press in milliseconds. And after the experiment, the participants compiled the qualitative questionnaires for the NASA-TLX, aesthetical rate, and preference. So this video is captured from the user's perspective, and you can see the test environment simulation with the virtual patient. And the participants confirm the location when the widget turns into green. Instead, for the AC weak collimation, they were provided with 5 collimation components, and when the components disappeared, the participants confirmed the tool positioning. So in the positional error results, we see that our hypothesis 1 is supported, that our widget has more precise and accurate than the golden standards. And also studying the positional error components, we see that PEX and PZ is better supported with our widget. Instead, also for the angular error, we see that hypothesis 2 is also confirmed, that our widget has more angular accuracy of 47%. And also studying the error components, we see that AE, X, and Z is also better supported with our widgets. And we see that the mandibular has better angular accuracy than the maxillary area. Instead, for the task time, we see that our hypothesis 3 is rejected, and our widget has increased time of 59%, so that it was slower than the golden standards. This was expected since our task required more precision, and we also see that mandibular condition is faster than the maxillary. Instead, for the NASA-TLX result, we see that our hypothesis 4 is supported, that ACV has less mental demand and frustration, and also for hypothesis 3 is supported, that had a better user-perceived performance. Instead, we see that ACV had increased physical demand of 64% and 19% increased temporal demand. So our main findings that our ACV surpasses the golden standard with better precision, accuracy, and acceptance. We see that angles and X and Z components are better supported with our widgets. We had reduced the mental load of 6% and 13% less frustration. We see that it's also less, that it's a user preference, that it's the added value. Instead, we see that our trade-offs are 64% more physical demand and 19% temporal demand. The users tell that we see the better Euler angles and tool without moving their head and better control of freedom. So for the future works, we would like to extend in 6 degrees of freedom, study the alternatives to linear gain, evaluate the user frame versus world reference. We would like to test in AR on the field and with experienced practitioners subjects. We thank for your attention, and we would like to discuss your questions.
Thank you very much. Let's a round of applause. We have time for one quick question. Go ahead.
Hello, thanks for the nice talk. Max Satkowski, Interactive Media Lab, Dresden. I'm no expert into dental medical work, but I'm interested into the system seems rather nice to help to orientate the tool that we need. However, I imagine as soon as I want to use it and therefore come in contact with the flesh and with the bone, there are some pressure of the tissue that could lead to movement of my arm again that should or could change my rotation and my positioning. How could you imagine that this could also be fixed, or is this even a problem? So as mentioned, I'm not really an expert in that part.
Yeah, you can.
Okay. So thank you for the question. So if I get right, you mean that the patient is moving and also the material is also soft? Yeah.
Not only the patient, but also if you put pressure on it, and then you have something, so you have to counteract the pressure that you have, and therefore you could lose this perfect positioning again. And how could this be fixed with your tool?
Okay. So yeah, question is great. Thank you for the question. So basically, the tool is much better than actually is happening right now. So maybe it is not, it will continue working also during the operation. So I think that is still a guidance. The reference is not the soft bone, but for this operation, you need to follow the bones, not the soft tissue. So that's the reference. And if there is some deviation during the drill, this tool will provide you feedback about what's happening. So it will guide you to control that. But actually, many doctors actually don't use any reference. They just go for, they remember in their mind where is the angle. In fact, there are some of these problems happening.
Thank you very much.
Thank you.
And another hand for the speakers. Okay, our final talk for the session is going to be online again, presented by Sabarish Babu, on comparing the fidelity of contemporary pointing with controller interactions on performance of personal space target selection.
Hi everyone, welcome to our talk. This paper is titled Comparing the Fidelity of Contemporary Pointing with Controller Interactions on Performance of Personal Space Target Selection, a collaboration between Clemson University, Carleton University, and National Young Min Jiaotong University, and I'm Sab Babu. So just a little bit of the background of the problem space. We are talking about on-air interactions with buttons on menu planes and personal space interactions that are very common in VR. And here are some examples. Personal space or near field is the interaction space that exists from the viewpoint to the limits of the operator's maximum arm's reach in VR. And that extends to about a meter or so, depending on the operator's maximum arm reach. And within this space, there are several popular commodity input devices available for personal space interaction. We are looking at the efficacy and speed accuracy trade-off of natural pointing with regards to low fidelity input device, such as the leap motion, which affords low cost, but there are tracking inaccuracies, and high fidelity, which could be like the glove, that are better tracking, but at a much higher cost, and direct controller-based interaction, which are readily available, but not very natural for use, since you're using it as a tool for interaction. Here are some examples of the pointing-based personal space interaction metaphor for menu selection and text area manipulation, and then controller-based personal space interaction techniques in a similar manner. With regards to related work, Tether and Stritzlinger in 2011 actually found that Fitts' law study on different input and interaction techniques in personal space found that haptic feedback was meant to enhance selection performance. Another related study, Lubos, Bruder, and Steinecke in 2014 found that the errors were greater along the viewing axis than along the movement axis when they were selecting targets that were centered at the hip rather than at the eye level or at the shoulder. Our research questions and hypotheses were as follows. We wanted to compare to what extent the efficacy of selection measured by linear relationship between movement time and effective index of difficulty via Fitts' law ISO 9000 standard differed between low fidelity and high fidelity pointing metaphors and controller input in personal space. We also wanted to find out to what extent the accuracy versus speed trade-off as defined by Fitts' law throughput was different between low fidelity, high fidelity pointing, and controller-based input in personal space spatial selection in VR. Our experiment design consists of the following. We varied the depth at which the targets were presented from 60% to 95% of the maximum arm reach, radial distance from 5 centimeters to 10 centimeters, and target width from 0.65 centimeters to 1.05 centimeters. As per the ISO 9241-9 standard of Fitts' law, we measured movement time, the effective user movement distance along the target axis, the over and undershoot of selection at each target location along the movement axis, and the throughput, which was calculated as the index of difficulty, the effective index of difficulty over movement time. The experiment design participants in session were as follows. We had 60% participants in study 1, 60 participants in study 2. The study was between subjects design across 3 conditions. In each of the conditions, participant had a total of 702 selections per selection trials. Study 1, 13 trials in each configuration of targets, of target distance by target depth, were presented in the same target plane. And study 2, the target distance by target width targets of 13 targets were presented such that from one target to another, they were presented at random target distances from 60% to 90% of the maximum arm reach. Here's a video of the simulation experience here for the controller condition, in which participants would, in study 1, select 13 targets radially presented via lateral movements in the same depth plane. And once they were completed with these 13 selections, then 13 targets in a different depth plane was presented, and they would continue with their selections. And then in the low fidelity pointing condition, you see that in experiment 1, a similar such design was employed, where the targets were all in the same depth plane for 13 targets. And then after 13 targets were selected, then targets were presented in a different depth plane, in which participants had to select targets by laterally moving their finger. And in experiment 2, participants had to select targets randomly from one depth plane to another within a 13 target configuration of target size and target distance, lateral distance. Okay. So you saw the point LF condition. Now the point HF condition essentially had the same virtual hand metaphor, and the pointer was exactly the same in all three conditions that was used to select the targets. This is the experiment 1 experience. And this is the experiment 2 experience, in which the 13 targets, each of the targets were presented in a 13 target configuration randomly from one target depth to another within the participant's maximum arm reach space. Okay, so the results of study 1, the multiple regression equation was found to be this right here, and this was highly significant with R squared of 0.43. Condition, effective index of difficulty, and target depth were significant predictors of movement time. By condition, we actually found that the controller condition and the point LF condition essentially had the slopes were, the point HF condition, the slopes were very similar to one another, with the controller, with the point HF condition having a lower slope as compared to the controller, and the point LF condition having a similar slope to that of the controller, but at a much higher intercept. And we also found that participants' slopes were significantly different in study 1. So with regards to multiple regression results by the target depth, we found that for the slopes were similar for 75% and 90% of the maximum arm reach, but the slopes was much lower for the 60% of maximum arm reach by target depth of the participants' reaches. Also, the R squared were similar for 60% and 75%, but was different and lower for 90% of the maximum arm reaches. In terms of throughput, we actually found a main effect of condition and target depth. Post hoc pairwise comparisons found that throughput for point LF was significantly lower than controller and point HF. And throughput at 90% of maximum arm reach was also lower as compared to 60% and 75% of maximum arm reach. And throughput overall was highest in the 60% of the maximum arm reaches and lowest at 90% of maximum arm reaches in all three conditions. For study 2, we found a multiple regression equation that was this right here. And this was highly significant. R squared was 0.225. A condition by effective index of difficulty interaction was found to be significant. R squared was 0.26. The slopes for the controller and point HF condition in experiment 2 was very similar, but the slope for the point LF condition was significantly higher, and R squared was found to be similar in all three conditions overall. And we actually found that the slopes were significantly different between the conditions in the participants' linear regression profiles that was found in the results of the study. Also, by studying the target depth, we actually found that similar to study 1, the target depth with the lowest slope was 60% of the maximum arm reach. Slopes increased to 75% and was the highest at 90% of the maximum arm reach. And also the slope for the intercept was the lowest for 60 to 75% of the maximum arm reach. And the slope was more or less at the similar to that of 75 to 90% of the maximum arm reach. But slopes for 60 to 90% of the maximum arm reach was the highest, and the intercept was also very different from 0 for reaches at this distance. Okay, and also a analysis of the slopes and intercepts was found to be significantly different by target depth overall. Okay, when we looked at throughput, we found a main effect of condition and target depth, and we found that overall, when it comes to throughput, the point LF condition was significantly lower than controller and point HF, and throughput for target selection at 60% to 75% of the maximum arm reach was the highest, and also throughput for 60% of the maximum arm reach was highest, and throughput within 90% of the maximum arm reach was the lowest. We also found that throughput for reaches from 60% to 75% was the highest, and throughput at distances from 75 to 90% was the lowest. We actually found that throughput within 60% overall was higher than throughput within 90% of the maximum arm reach. So overall, we found that condition was a significant predictor of movement time. Participants took more time to select targets in the point LF condition as compared to point HF and controller condition. Throughput was higher in the controller and point HF condition as compared to point LF condition. One reason for this is that the point LF condition, the latency and low frame rate could have been detrimental to performance. We also found that target selection within the lateral movements and between depth planes in the center regions of the maximum arm reach in personal space was more efficient and produced higher throughput than selections at the furthest edge of our maximum arm reach. So finally, we found that minimizing latency in popular commodity vision-based gesture tracking systems could improve selection efficacy and speed accuracy trade-off. With regards to menu placement and hierarchical menu placement, placing these menu buttons in depth planes at the middle and of the middle regions of the maximum arm reach was found to be much more efficient, and speed accuracy trade-off was the highest. Future work will focus on raycasting versus pointing versus controller-based target selection in personal space interactions. With that, I thank you for your attention.
Thank you. Thanks for the round of applause for our speaker. And now it's time for questions. Yes.
Thank you for your presentation. I have a question about, can you explain a little bit about the rationale for choosing the specific independent variable numbers? Like, why did you choose 60, 75, and 90% as the numbers? And the second question is, I think 702 pointing tasks are a little bit harsh on the participants, and was there any fatigue effects observed in the experiments? Thank you in advance.
Thank you for these questions. I really appreciate it. With regards to your very first question, the rationale for the independent variables, that is with regards to target depth, from 60% to 90 to 95% was actually chosen because if you choose a target depth, we have been doing near field personal space interaction research for a very long time. And if you choose target depths that are closer in VR, that is, then 50% of your maximum arm reach then there is the risk that participants may then take their controller and hit it against their head-mounted display. So oftentimes, in order to avoid that, there was a minimal displacement of the nearest target along the depth plane of at least 50%. And just to be on the safe side, we chose that nearest depth plane to be at 60% of the maximum arm reach. 90% of the maximum arm reach is very close to the critical or maximal reach boundary. So from an ergonomics perspective, we didn't want to extend it to very personal space in which participants had to actually shift their body or move at the hip in order to make a selection. That is, of course, interesting for future research, but we wanted to study this particular region of space that is our personal space, or up to the maximum arm reach per se. Because when it comes to peripersonal space, one could also take a step and then bring those objects that are in the peripersonal space into personal space and make selections there. Now, with regards to your second question, 702 reaches, I understand, could be potentially fatiguing to the participants. Participants did not complain about fatigue per se. We also did a NASA TLX assessment at the end of the study, and we did not find that participants rated on the physical demand characteristics of the experiment highly. And once they got to a certain number of trials, we asked participants if they wanted to take a break. And if they wanted to take a break, they took a break for about 5 minutes, and then they continued on with the experiment.
Okay,
but others in Fitts Law research have done sort of 3 sets of trials and sometimes up to 1,000 trials or so. So it's not as taxing as you might think in classic Fitts Law research.
Thank you very much. And so that concludes the session. Let's have a round of applause for our last speaker.
Thank you all.
And at this point, before the keynote at 3 o'clock, I should notice that we have now, starting for an hour, a full house of sponsor exhibition, posters, tea break, demos. It's, I think, the only session time that's straight across the board. There's all kinds of stuff going on besides food. So look forward to seeing you out there and see you at the keynote as well.
Good afternoon. I hope that everyone enjoyed your last night's social event. And welcome to attend the second keynote at the ISMAR 22 to be given by Professor Mark Polofey. And the title for Professor Mark Polofey's keynote is Towards the Industrial Metaverse. Okay. Before we start, I'd like to give a quick introduction about Professor Mark Polofey. Maybe some of you have heard his name or have seen him many times. So Professor Mark Polofey is a professor of computer science at ETH Zurich and the director of Microsoft Mixed Reality and AI Lab in Zurich, where he works with a team of scientists and engineers to develop advanced perception capabilities for HoloLens and mixed reality. He was elected as the IEEE Fellow in 2012. He got his PhD from KU Leuven in 1999, and before he joined ETH Zurich, he was a professor at UNC Chapel Hill. Professor Mark Polofey is well known for his excellent works in 3D computer vision, having been the first to develop a software pipeline to automatically turn photographs into 3D models. He also works on robotics, graphics, and machine learning problems. Other noteworthy projects he works on are real-time 3D scanning with mobile devices, a real-time pipeline for 3D reconstruction of cities from vehicle-mounted cameras, and camera-based self-driving cars, and the first fully autonomous vision-based drone. Most recently, his academic research has focused on combining 3D reconstruction with a semantic scene understanding. Without further ado, let's welcome Professor Mark Polofey to start his keynote. Mark, I leave the floor to you.
Thank you. Okay, so let's see. So can you all see the slides? Hello?
Yes, very good.
Okay, fine. Okay, so I'm really grateful for this opportunity to present at ISMAR. I'm very sad that I couldn't make it in person. This is in the middle of the semester for us, and so travel is somewhat limited at this point. But yes, so I hope I can give you an interesting talk. In particular, I'll talk about essentially all of this technology that we're developing towards developing the industrial metaverse in particular. So there's lots of interest, of course, these days in what's possible in the consumer space. In many ways, we believe a lot of the kind of real, that this will still take many, many years to really fully realize its potential. And I believe that the first places where we really start seeing very valuable applications is really more in the commercial space, in the industrial space. And so I'll discuss a little bit what we're doing there. Maybe first to put the big context, what we really see is in the context of personal computing, we really look at devices like first generation of personal computing devices as PCs. Those are great machines at manipulating digital information, but are kind of not connected to their environments. Second wave of personal computing devices is really these type of cell phones that everybody now carries with them. Those are small computers. They're in many ways worse computers than your PC, but they are computers you always have with you in your pocket. Those are computers that have some awareness of the environment, like for example, knowing where you are, and therefore for GPS, and therefore can better assist you with some tasks that have to do with the world, like navigation through the world. If we look at then the next generation of that, we're really talking about devices like this one here, devices that allow to place information anywhere in front of your eyes on the scene. They also have tons of sensors here, and those sensors mean the device has much more awareness of the environment around you, is also observing what the user is doing, and so therefore can much better assist, much better mediate all the information and combine it with the real world context in front of the person and the task that the person is trying to execute. And so we really see this as the next natural wave for personal computing devices with a huge potential. If you look at the device here, so HoloLens 2 is a device I worked on while I spent 2 years in Redmond with Alex Kipman. I developed together with the team. We looked at developed a lot of the computer vision algorithms that are embedded in there. And I actually want to a little bit open up the lid and look inside HoloLens to give you some idea of what's all going on there and how the device can actually on a tiny battery for several hours deliver all of this always-on real-time computer vision. So if you look at the sensors embedded in here, there's of course a color camera. This camera is actually a user-facing camera, or it's a camera that's meant for applications. This is the one camera that's accessible normally by applications. This allows to essentially share the viewpoint of the person, of the user of the device, share that with remote people, so that remote people can have an understanding of, can have the same context and can assist the person on site. But besides that, there's lots of other sensors built in. In particular, there is essentially a rig of 4 cameras. The 2 central ones provide a stereo view with immediate depth computations from the world in front of the device. And then there's 2 additional cameras that provide a wider peripheral field of view. And this is combined with inertial measurement, an inertial measurement unit, so accelerometers, gyros. In many ways, in the same way that we use our eyes and our inner ear system to feel motions, this is the same for the device essentially. The central stereo allows to build up a map. It's a head-worn device. You can very quickly turn your head. So having peripheral images allows to keep track of the map that we are building as we walk around. The reason we need to do this, I mean, as I assume all of you know very well, but is essentially that if I want to place holograms in the world in front of me, if I just place them there and then move my head, the holograms, you know, they're displayed here, and therefore they would just move with me. So if I want to place them in the world, I need to essentially compute the motion of my device so that I can apply the inverse motion to the graphics so that it looks like it stands still. And of course, to do that effectively, I need to do all of this at very low latency. Or actually what I need to do is to compute forward and predict forward, and then maybe use some latency hiding capabilities to hide maybe the discrepancies, or to hide some of the latency that would occur by just computing motion, rendering, and then coming back to the display. There's a few tens of milliseconds, but HoloLens has built-in hardware to then leverage the IMU results, which are much lower latency, and do a small correction, a late stage reprojection, as we call it, to essentially hide, to do an image-based warp, to essentially correct these the discrepancy between the forward prediction and then the actual observed motion at the last second, or the last millisecond, let's say. So this brings the whole latency below 10 milliseconds. Now, one thing that's interesting is if we look at this motion computation, there are actually scenarios where this actually doesn't work as well. So pretty much all the devices use visual inertial motion tracking, because the visual sensor or the inertial sensor is great at low latency motion estimation, but drifts. Visual sensors allow to compensate that drift. But there are, of course, situations where those two don't agree. In most places they do agree, but in all the situations where we tend to get motion sick because our visual signal and our inner ear system don't agree, for example, in a moving platform, in a moving vehicle, you see a few examples here, then actually also the tracking of visual inertial systems also fails. This is because essentially the visual motion, which mostly sees the inside of the vehicle, and the inertial motion don't agree. And here you see a few examples. So in HoloLens now, you actually have a moving platform mode where we actually allow those two signals to disagree, but we model the discrepancy between the two. And that way we can actually stabilize holograms also in those moving environments. We did this partially. We tested a lot of this with Volkswagen, that was very interested in using HoloLenses for example, of course, down the road when this becomes consumer devices, to of course enable these applications. But in the shorter term, more in the context of being able to prototype heads-up displays, which are fixed mounted in the vehicle. Those take a lot of space in the vehicle. They want to pre-visualize the interfaces, how this will look, what it offers. To do that, use HoloLens, but then the problem is that HoloLens was losing track as soon as the vehicle was moving. And so they were interested in solving that. We developed that. What you saw at the bottom here was essentially our developer in Zurich testing this capability himself in the trams. Where you see that the tram is actually accelerating and slowing down at all the tram stops, and the holograms actually stay stable. What you see at the bottom is actually, in the meanwhile, the main application of this in the current setting is really on ships. Also on a ship, just with wave action, the device would continue to lose track. That's what you see on the left. That's a normal HoloLens operation. You can actually can barely start your menus and it's already losing track. But then on the right, you can actually see that once moving platform mode is switched on, this actually works in a quite stable way, and you can actually utilize HoloLens. Now, why is this important? Well, as we'll see in a second, we have one of the main applications for HoloLens is really to bring in a remote expert to help you with a problem. And when is this most valuable? Well, it's most valuable when it's really hard to get an expert on site. And there's essentially no harder place to get to than a ship at sea, And so if a machine breaks down on the ship, you can actually, with a satellite link, communicate and get help to fix the problem. But and so HoloLens is actually great in those scenarios. But until now, you just couldn't keep the hologram stable. The experience would just fail to start properly, and that's something that's been resolved in the meanwhile. Okay, so besides that, there's many other sensors still on the device. So in particular, this depth camera. This is essentially the same camera as in the Azure Kinect. It was actually developed for HoloLens, but then given the camera worked really nicely and is essentially one of the best cameras out there for 3D perception, it was also provided in the Azure Kinect development kit. What you see here is essentially it's time of flight. So essentially there's several images being sent out. Those images have modulated light. So if you look, actually, I hope you can see my cursor. You have essentially a camera over here and then two illuminators. And essentially what happens is on the same clock, we send out light that's modulated at a certain frequency in the order of 100, 200 megahertz. And then the pixels themselves also get modulated. And so if the light comes back as it bounces and oscillates at this frequency, and the pixel also oscillates, if they're in sync, when the pixel opens, there's light coming in and so on, then you have a strong response. If they're out of sync, then essentially whenever the pixel opens, there's no light and vice versa. So we can essentially directly measure electrically the phase difference, observe the phase difference on a per pixel basis for the light traveling and coming back to the device. And so that's essentially a great way to measure the phase. If you do a few different phases, phase offsets, and a few different frequencies, you can uniquely determine the depth with the sensor. And so that's what you see on the right. You see essentially the illumination. So there's a spotlight. There's these two illuminators are spotlight illuminations with this modulated light. And then on the right, on the left here, you can essentially see the depth response, which has two modes. One is wide field of view, high frequency, and one is narrow field of view, but more energy, so can perceive depth until further away, but then at a lower temporal frequency. So first application is to actually reconstruct the environment, as you see here. So HoloLens in the background, as you use it, is continuously reconstructing the environment. You can wonder, why do we need that? Well, it's essentially so that we can provide a true mixed reality experience where the holograms can actually interact with the physical space. For example, you can have avatars walking on the ground, you can have objects that sit on tables, you can have occlusions simulated between real and virtual objects, etc. So for that, we need the geometry of the scene. And so that's being reconstructed in the background all the time. And so those meshes can be accessed through APIs. You could essentially integrate that into large-scale reconstructions or floor plans or things like this as a byproduct just of using the devices in those spaces. Then, of course, we have also hand tracking. So that there the camera is at a much faster frame rate, so it's up to 45 frames per second perception. Then we have a DNN inference core included in HoloLens that will actually find the hands, detect the hands, find key points on the hands, initialize the hand poses. And then in a second stage, there's essentially a geometric fitting algorithm that will fit the hands quite precisely to the geometry that's been observed. The small offset you see in the video here has to do with the fact that on HoloLens, we actually borrow one of the displays in terms of the mixed reality content, but we overlay that on the camera here. And so there's essentially this baseline here between the eye and the camera. But if you actually experience it yourself, there's actually no discrepancy. There's no offset between this. Okay, so that allows natural interaction with holograms. You can grab holograms with your hands as if you were essentially manipulating real objects. We also have eye tracking built in. So these are essentially those two cameras over here next to the nose. They look at the eyes. Along the rim of the display, there are a number of LEDs, infrared LEDs, so you don't see them, but the camera can see them. They reflect on the eye. They allow to determine precisely where the eye is, and then we can detect where the pupil is and use that to find essentially quite precisely in the order of a degree the direction of the eye gaze direction. Now that's not the, so, you know, one of the applications for that is here as a nice little example is essentially as you read text, it can automatically scroll the text along in mixed reality. But actually, there's two other applications that are at least as important. The first one is that we can actually read off the iris of the person and therefore do biometric authentication for the device. And then the second application is really the display calibration, because it's really important in particular to know the distance between the eyes, because people have eyes, the so-called interpupillar distance, have eyes at different distances. And that essentially directly corresponds to our feeling of depth. The way we perceive depth is based on essentially a stereo rig here, or two eyes. And depending on the distance between the eyes, we perceive depth. If the distance between the rendered images is not the same as the distance between our eyes, between our pupils, then we will essentially perceive the scene to be too big or too small in terms of our stereo perception. However, we have a second way to perceive depth, which is by just moving around. And then if those two don't agree, this will create discomfort. And also in particular, if you try to press a hologram for, you know, like a button, for example, if you try to grab a hologram or press a button or something like this, if the depth perception is off, you will actually have, it will disturb the experience, because you might think you're pressing the button based on your depth perception. But if it's off, the button might be further or closer, and this might essentially ruin the experience. So all of these things are really important to give you the right experience. It is also, of course, microphones built in. Won't talk about that, but it enables HoloLens to really understand people even in very noisy environments, because there's microphones close to the mouth and then environment microphones that can separate environment noise from what the person is saying. To make all of this possible, one of the key elements is the HPU, the holographic processing unit. This has essentially lots of different compute blocks. Those are mostly DSPs that run things like surface reconstruction, head tracking, eye tracking. There's the raw to depth for the depth camera, so raw signal to depth computation, audio processing, etc. There's a special block that is there for DNN inference, so very low power inference for the networks for perception. And then there's a big part of the chip also dedicated to depth-based LSR. So that's the late stage reprojection. This is really the component that allows us to hide the latency. So even if we have tens of milliseconds of latencies from motion to photons on the display, we can actually bring that down in terms of perception to below 10 milliseconds, meaning below where we would perceive any latency. So this chip is then complemented with a normal Qualcomm processor SoC in the back, which is the one that has the CPU, the GPU, and runs all the applications, essentially. So what can you do with this device? Here's a few of the key applications that are in use today. Here's a remote assist application. This is actually in Mercedes-Benz in the US, where they have essentially experts at the central location that can assist technicians all over the US in all of the dealerships to solve more complicated cases and essentially provide technical assistance to the person on site for repairing the cars efficiently and not creating problems. The other application, so that's one is this technical assistance by an expert, by a person. The other one is for more repetitive tasks that people have to learn many times over. Different people, lots of people have to learn to do the same task. Think also in the car industry, for example, some maintenance task, when a new model comes out and there's a new procedure to do maintenance, then you would want to actually record a mixed reality tutorial, as you see here, which is much easier to understand than a paper or video tutorial. Essentially, step-by-step instructions overlaid on the actual machine, aligned with the actual machine, is a very, very powerful application. One of the challenges with this is actually to generate those tutorials. This can be quite time-consuming. You need often the assets of the different machines and so on, digital assets that represents the different pieces and machines, things that have to be manipulated. So here's an example of some explorations we do of just recording by using the depth camera, the RGB camera, just recording what a person is doing. Let me replay the video. What a person is doing, and then just segment the parts of the hands and the objects being manipulated, have those automatically aligned to the machine of interest, and then essentially provide a replay of the experience so that a student can essentially just see this and then repeat the actions. So this would really greatly reduce the cost of developing those tutorials. But another thing that we're also looking at, and this is much more on the research side, is really looking at being able to close the loop. So currently HoloLens or other mixed reality devices are great at providing you step-by-step instructions in the physical context, but they actually, while they do hand tracking, they actually don't really understand what the person is doing. So we can't really close the loop on having the device kind of follow along the instructions that is providing to the person to actually check if the person is doing them correctly and understand what the user is essentially doing. So we're doing research in that space on seeing how we can make essentially do first-person egocentric action recognition. And here's just some recent work that we just published that is essentially to enable us to train more easily. So we would have one reference sequence, for example, here of a pouring action, and then we can provide to enable self-supervised learning. We can, here as an auxiliary task, we do automatic alignment of other pouring sequences to this one sequence. And then we can use all of this data then where we only had to label one sequence to learn action recognition. Here's another example of people moving around, which was also published at CVPR most recently, also in terms of automatically aligning different sequences of people based on skeletal motions. Here's then a kind of practical showing like how this could practically be used for this type of tutorial. So here you see a simple tutorial that's essentially giving instructions of how to replace a printer cartridge for a printer. And you see essentially that we can automatically follow along the different steps. And so the device can automatically detect if the person is going through this 6-step procedure in the right order and do that properly. So here's an example when something goes wrong. Here a person makes a mistake, so opens this, but then doesn't open the actual printer cartridge lid. And so the machine can actually, HoloLens can now detect this and can essentially provide corrective instructions for that. Okay. So there's lots of applications in many different fields. There's a lot of interest and a lot of opportunities in medicine. In general, HoloLens is really aimed at what we call first-line workers. These are people that work with their hands in the world. So of course, one of the most high-value places where people work with their hands is in surgery, in the medical field. Here's just a few examples. Here's a specific example in Zurich of our colleagues at the Ballroom University Hospital, so our collaborators there. And this was a world first type of spine surgery that was assisted with HoloLens. It switches back between cadaver tests and then the actual real surgery in the video. So essentially the key is that you have to bend a metal bar to fit exactly where the surgeon has put screws in the different vertebrae of the spine. And so he has to bend it exactly in the right shape. And here HoloLens can assist him in essentially getting the right shape from the first try, instead of having to typically try it out, try to force it in. If it doesn't work, go back, bend it a bit more, go back and forth. Here, HoloLens allows to measure precisely the desired shape and then verify visually that that shape is achieved before trying to put it in to fix it in the patient. Here's some of the research work we're doing. We're actually going to do, we just started a big project in the trying to track and monitor a surgery and then essentially stream that and use that for education so that you can virtually bring in medical students in the OR, either at live or also delayed, and have them watch an annotated surgery to learn from themselves. If you're interested in doing research for HoloLens, it's a great platform to capture lots of, with all those sensors that I explained before. We actually provide access both if you switch a device in research mode. It's a great device for doing egocentric computer vision. You can get access with research mode to the depth, both short and long throw. So the wide field of view up to 1 meter for example, hand tracking, or the more narrow beam that goes up to 5 to 7 meters. Depth perception. You can have the grayscale cameras that are used for tracking. You can have access to the IMU, the inertial measurement unit, while at the same time still having access to all of the APIs for hand tracking, eye gaze tracking, head tracking, and also have access to the RGB camera. Here's an example of some of the things you can do with that. So you see a visualization here. So the data was used to build a 3D model of the background here. You see the head pose, you see the cyan line and dot is the eye gaze, and you also see the hands here floating around. So all of this can be obtained from the HoloLens sensor. There's also so there's quite some support software to enable you to do that, also to stream it off device with the MSR has a PSI platform for situated intelligence, and that also facilitates lots of those experiments. Now that's a device. There's lots of things that become possible if we combine this with the cloud. One of the examples is actually to go beyond the capacity of the device to do to render. So on device, you can render in the order of a few 100,000 polygons at most in terms of complexity, because it's essentially a small GPU that's mobile GPU. But because of the latency hiding hardware, we can actually also ask the cloud to render GPU in the cloud to render much higher, much more detailed models. Here it shows 100,000 polygons, 100 million polygons. I know that there's you can do billions of polygons or raw point clouds without needing to decimate them, and essentially visualize this fully interactively on a HoloLens device by streaming it from the cloud, and still have a fully natural interactive experience by leveraging the this hardware that can hide the latency and leveraging the depth-based late stage reprojection, which is essentially this small image-based warp that will correct from the computed predicted pose to then the actual pose that the device at the last few milliseconds has computed. Okay, so then another aspect of that the cloud can support is really supporting communication scenarios. So Microsoft Mesh essentially enables to have multiple people communicate and feel present and interact with each other, even if they are not in the same place. As you see illustrated here, this can both be done with HoloLens devices as well as with VR devices, in particular if people are remote. And you can actually try some of this in the Microsoft Mesh app if you happen to have a HoloLens. Here I'll show a little video, and there should be sound that essentially explains what the metaverse is, and then we'll continue after that.
Simply put, a metaverse is a digital space inhabited by digital representations of people, places, and things. Think of it like a new version, or maybe a new vision of the internet. Many people talk about the internet as a place. Now we can actually go into that place to communicate, share, and work with others. It's an internet that you can actually interact with, like we do in the physical world. And it's not just a vision anymore. Right now, you can go to a concert and experience a show with other real people inside a video game. You can walk a factory floor from your own home. You can join a meeting remotely, but be in the room to collaborate with your coworkers. Those are metaverses, and the future is already here.
Okay, so, oops. So that's one definition of the whole of the metaverse. Here's another illustration.
Welcome everyone to the end floor.
Of how this is used on top of this essentially an Accenture demo. This was also shown in at the World Economic
Beautiful.
It enables people to essentially have an experience together. It's built on top of the
Hey, do you guys want a group
platform. It just shows you, some of those experiences. Of course, we have still a long way to go to really bring full presence along. Here's a few examples of some of the technology that my colleagues, in particular in our Cambridge research team, are working on. So here's the Tom Cashman, essentially working with the HoloLens, and just from the HoloLens signals, we can drive a quite realistic motion of the avatar. Here's just from actually work that's being published next week at ECCV. Also from my colleagues, some of them here in Zurich, some of them in Cambridge, essentially doing, leveraging really dense landmarks on faces to do much higher quality tracking while still having very low power requirements so that this can run on at more than 100 Hertz on a single CPU core. And really the key to doing this was to leverage synthetic, high quality synthetic face renderings to essentially train algorithms to do dense feature tracking. But what I wanted to talk about for the rest of the talk here is really more a focus on the spatial computing, the spatial intelligence. So for scenarios like the one you see here, it's important to be able to share and persist information across devices, across time, and across larger spaces, and do that in a reliable way. And so conceptually for that, what you want is essentially every device, when it navigates a space, just to operate, augmented reality device, mixed reality device, need to build a model of their environment. Typically that's done on device. Every HoloLens is building that in the background. Every AR kit, AR core, other device is kind of building a small map on device. Now, of course, there are limits of how well this can be done because of the real-time requirements on device, et cetera, et cetera. So the concept is essentially to move these maps to the cloud. As another device maps another part of the space, we essentially, over time, can puzzle back together in the cloud a high-quality map that essentially integrates all of this data from all these different devices and can also essentially do lifelong mapping and keep a map up to date and keep merging new data with much less constraint in terms of computing than what you would have on the devices themselves. And also just the size of the map that you can accumulate just goes well beyond what a single device could really handle by itself. Here's an example of this kind of building. This is Studio A on the Microsoft campus where the team was based at the time. These are just relocalization features here being actually shown, so not a full dense reconstruction. Initially, we used this service to enable to power Minecraft Earth, which was an augmented reality game. Here I was playing in Zurich, here a few 100 meters from here. So this game enabled people to play together, to share locations, etc. Sadly, this was done just before COVID, and then everything was discontinued as lockdown came in. But what we really focused on is really more these type of scenarios that I showed before. So it's really about having people be able to go, in terms of more the industrial metaverse, essentially being able to go across a factory floor and get access. So today, there's lots of sensors being built in. Those are digital sensors, typically called IIoT sensors, so Industrial Internet of Things, essentially making digital measurements on the machines and providing that for, to the control room, providing that to AI capabilities to do preemptive maintenance and things like this to enable all of this. But typically, all of this data is not available on site to the frontline workers, to the people that are actually manipulating and working with those machines and have to maintain the machines. So the key is to really able to bring all of this information back in its spatial context and make it accessible in a very simple way and provide all the rest of the relevant information to people that are working across the factory, and also provide essentially the right views and able to provide the right views based on the function of the person to augment the scene with the relevant information to the task at hand. Here's another example. There's also a HoloLens essentially, but a version for with a built-in helmet. This collaboration with Trimble, as you can see here. But essentially, it's a HoloLens 2 with a hard hat. For example, for construction sites, where you can then compare the plan, the digital plan, to the actual construction, and look for discrepancies, understand the context of what you're supposed to build, etc., etc. Okay, so here's a few examples of this mapping in action. This is the main train station in Zurich, very complex building with multiple floors. There's a whole mall essentially built under the train station. And then essentially this is a map that we built just by walking around the space with HoloLenses. We actually did that at night to make sure to, in terms of privacy, to not record people, because for testing, we recorded all the raw data of the devices. So we did this between 1 and 4 a.m. Together with people from the railways that were interested in our experiments. And essentially what you see here, all the different color curves are how we walked around the space. So we had half the team, walk around with HoloLenses and record all that raw data. And then essentially our cloud computing, distributed cloud computing platform merged all of this into one single consistent map of the train station, as you can see here. And so once you have this map, this allows you to attach to this essentially holograms or information, and then persist those and share those back from the cloud to devices. Here's in the industrial context another example. This is a milk factory in Switzerland from Amy. They produce essentially drinks and ice cream and other things in this factory. And so we walked across the factory also here with devices. This is a factory that's larger than 100 by 100 meters. So it's 10,000s of square meters, 100,000s of square feet of scanned surface area that we reconstructed just by having a few people walk around. It's a few hours of data collected by just walking all around the factory in a relatively natural way, and just looking around and reconstructing essentially the whole three-dimensional space from that, and therefore be able to realize that scenario as we showed in the first case. Here's also an interesting combination. So if you really want to provide remote access to the factory, while you could potentially do that from the HoloLens sensor data, if you really want at every location have a nice 360 view and colored high quality color 3D reconstruction of the whole environment, also sometimes outside the range of the depth cameras from HoloLens, then these type of professional capture devices can be the right thing to use. But the key is you get a lot of extra value if you can combine this with also. So this is for remote people, but if you can connect that back to the on-site people that use HoloLens, then you get something even more powerful, because then you can really have remote people have this visual model as a spatial context, and have the people on-site, look at the real machine. But if we can align our HoloLens maps, in this case, what you see is an automatic alignment of the HoloLens map, all the green dots and the different colored dots here. That you saw here, green and cyan dots, correspond to HoloLens poses from the previous map that are automatically aligned because it's all based on image data. We can do an automatic alignment between the HoloLens maps and then this, in this case, Navis scan of the factory. And therefore, we can have remote people and on-site people have the exact same spatial context and facilitate communication between them, and again, having people solve hard, challenging tasks, repairs, and things like that by bringing in remote experts that get the full spatial context and information. Here's an example and showing, showing here how we can easily also fuse not only multiple HoloLens devices, data captured from multiple HoloLens devices, but also here handheld Leica scanner, as well as robot scans. So the Boston Dynamics Spot Dog, you can actually see on the lower floor, you can see different heights. So there's the robot is the lowest, the handheld scanner, and then the head-worn scanner for different heights of people. That were all the different heights you could see here. So we can automatically merge all this information in a single consistent map. which means that it allows us to have robots and people all be co-aligned, and then be co-aligned with essentially a visual representation captured by this reality capture device, and have essentially all of this, enable all of this to have, you know, a common spatial coordinate system. Also, of course, we can augment the relocalization maps, these feature point maps, with then LiDAR data, as you see on the top. This is our spot robot, had an Ouster LiDAR mounted on top, and so we can integrate that data and put it on top of our relocalization map, as you see visualized here. At the bottom, you see actually the same. These are the office where I am now. I'm actually here in this corner up here. You can also get these type of reconstructions from HoloLens data, from the HoloLens depth camera. And here's actually on the right is this kind of bigger space during construction, also reconstructed from HoloLens, purely from HoloLens data, leveraging depth camera. If you're interested in that type of space, large scale, mixed reality mapping and relocalization, then I invite you to look at our most recent benchmark that we published, that we will publish next week at ECCV. So it's called Benchmarking Localization Mapping for AR, in short, LAMAR. And so you can find all the information at lamar.ethz.ch. What we did is over more than a year's time, we collected data in these sites. We both collected data with high-end Navis scanners, which we use as ground truth. These are the images you see here, actually visualizations of the models we captured with the Navis scanners. There's both a trolley as well as a backpack system. This provides us ground truth, and then we aligned very precisely all of the HoloLens and mobile phones or tablets were automatically aligned to that, and that provides us then ground truth information, and then we let people do queries and validate how well they can localize to the data. So here's actually a video explaining some aspects of this.
All trajectories are globally registered with centimeter accuracy by fusing the AR sensor streams with the ground truth laser scans. Despite challenging viewing conditions, the process is entirely automated and requires no manual annotation of any sort. We therefore know the pose of each sensor measurement, but also the detailed 3D geometry of each scene. The accuracy can be verified by comparing the captured images with renderings of the 3D models using color or depth.
Notice we do this over time, and so there's sometimes actual changes.
We evaluate state-of-the-art approaches to localize images from different devices in a given crowdsourced map. We measure the recall of the estimated query pose at 10 cm and 1 degree, an accuracy required by most AR applications. Existing academic benchmarks focus on localization with single isolated images. Considering the additional sensors available on AR devices, we can significantly improve this low performance. First, multi-camera rigs are significantly more accurate than single images. Second, we can leverage radio signals to constrain the place recognition. Third, we can leverage temporal streams by combining multiple images with local odometry poses. Here, sequences of just 20 seconds yield a large boost. Last, both radios and sequences can be combined. This shows that the single image setting is artificially difficult and not representative of practical AR systems. Yet, the problem of localization is not solved, as almost all queries share some visual overlap with the map and are therefore localizable. This upper bound shows that further research on image matching and optimal sensor fusion is needed to make localization ready for AR. For a compelling user experience, applications should strive to retrieve and visualize content as quickly as possible after starting a session. To quantify this, we introduce a new metric, the time to recall, which measures the sequence duration needed for successful localization. Here, localizing a phone requires at least 6 seconds in 60% of the queries. Using radios reduces this to less than 3 seconds. LAMAR is the first benchmark that faithfully captures the challenges and opportunities of AR for visual localization and mapping. The dataset, ground truthing pipeline, and benchmark are all publicly available. Thank you for watching.
Okay, so if you're interested, please check that out. There's also a whole line of work that we've started exploring, looking at if you actually want to use a map for relocalization, that map, depending on the scenario, could could be a privacy concern. For example, here you see someone that enables a mixed reality experience in their bedroom, for example, and this this map of the bedroom itself could reveal essentially might not be something that people would be prepared to share. So, for example, so the question is, can we, if we have a space that might be confidential in terms of its geometry, in terms of its spatial arrangement, can we actually still enable localization, but in a representation that doesn't actually reveal the geometry of the scene? And so what we proposed was to switch from using 3D points for localization to actually forget the precise location of the point, but switch to a line representation. So if I project a point in an image, I have two constraints. Wherever the point lands in XY coordinates is a constraint. That should be the same as the actual observation in the image. So I have two constraints per point. If I relax and I don't say exactly where the point is, but I just give you a random line going through the point, and I say somewhere on this line the point is located, then I get a kind of a line cloud which cannot anymore visually be interpreted in terms of what the geometry of the scene is. But that line projected in the image still gives me one constraint on the location of the camera. So if I now have, for the general 6 degree of freedom, if I have 6 of those lines, so 6 correspondences between the lines with the descriptors of the original points and the 2D points observed in the images, I can actually compute my location exactly if there's no noise, while not sharing the geometry of the scene in the map. We can also do it in reverse, which is if I upload images, I don't upload 2D features, but I upload 2D lines, which again can hide essentially the content of the picture itself that the features that I upload. So just from the features, you can actually do an inversion attack, which, the original is on the left here. The middle column is if you run a kind of an inversion attack on the features. So just uploading features, you can actually mostly invert the image back. But then on the right, you see with a privacy preserving technique that much less can be inverted. And in particular, all of these spurious objects that are typically the ones that that are the ones that privacy concerns are associated with. It's like the people in the scene, etc. Those can actually not be reconstructed anymore. Okay, we've actually done we've done a lot of work in this space. We've done full structural motion pipeline. What you see is that from the structural motion, you can reconstruct classical, you can reconstruct lots of things on the left. The privacy preserving ones, you can see any person here also showing up. So there again, privacy is preserved. We've actually also extended that concept not only to the geometric location of the features, but to the actual feature descriptors. Also essentially lifting those from a single point, a single vector in a high dimensional vector space, describing being a feature descriptor, to essentially generalize that to a linear subspace. But a well-chosen subspace that essentially also helps preserve privacy, but still enables to match features. We've even applied that to face recognition, and we can hide gender, for example. So in a database of encrypted faces, if you don't do anything, you can, from that descriptor, you can, with a high likelihood, guess the gender of the identity of the feature, the face, the vector associated with a particular face. We actually have the ability to hide particular features like gender in these databases while still enabling matching. The last thing I want to talk about is the combination of mixed reality and robotics. I already hinted at that in the mapping, that we can merge maps of robot sensors and mixed reality device sensors. But if you look at the capabilities that this enables in terms of human-robot interaction, if you want humans and robots to interact in a spatial context, being able to share coordinate systems is essentially table stakes there. And so that's what we're looking at providing. And so you see this illustrated here, the person with the HoloLens points to a particular location, target location for the robot. The HoloLens itself can interpret where that location is in its own coordinate system. So if you point somewhere, it sees the pointing, it can interpret that, intersects the kind of ray of the finger with the ground, determine the 3D position in own spatial coordinate system over this Azure Spatial Anchor ability to share coordinate systems that can be transferred to a global coordinate system of that environment. And then the robot, if the robot can also localize itself with respect to those maps, then the robot can go to that target the robot can actually plan its route, can visualize that route, or can send that route back to the HoloLens, and that route can be displayed. And so the person can know what the robot will actually do, and therefore both can work together seamlessly. Here's a visualization of this. This is Eric, someone on our team, who's essentially here working with Spot, the dog from Boston Dynamics. And so here you see how he's essentially defining in mixed reality a mission, and then Spot is executing that, and this gets visualized here. So this is a very small, but you can do this on much larger spaces. Small mission that he planned here, where the robot is essentially going from predetermined viewpoint to viewpoint, where Spot, one of the applications of Spot is to do an inspection round autonomously. And that's what you see here. So here's actually a slightly more advanced version of this. We mapped out the space. This is a top view of the map. Again, just feature locations. And then in here, you can define essentially a number of target locations directly on the map. And then let me go a little bit faster in this. Here you then see Spot, actually, let me get the beginning here. So Spot autonomously stands up from its docking station, and then essentially autonomously starts executing the mission here, and goes, let me show you here, essentially starts walking for offices, and essentially does this fully autonomously based on the map essentially here. And this is the trajectories themselves are just determined from, are essentially selected from existing trajectory snippets in our motion graph for navigation. So the last thing in terms of robotics, you can also enable remote action of people potentially, as in this example where you have a person wearing a mixed reality device and then you enable a person remotely to actually do particular activities and interact with the environment. So here's an example of a colleague at ETH. So there's a collaboration with ETH with Professor Stelian Koros and his senior researcher, Roy Paran. This is Roy actually testing the system. So the robot is located somewhere else. And so here, Roy is using the HoloLens. The hand tracking is used, and the hand tracking is mapped to the actions of the robot. The head motion is actually coupled to the stereo rig mounted on top of the robot here on its own robot arm. And so when Roy moves his head, the robot actually also moves. And so that way, he essentially really embodies the robot and can essentially act in a relatively natural way in the remote environment by just having his hands connected to the robot hands. Of course, lots of challenges in making this work really effectively in terms of latency and other aspects here. But also the fact that the arms of the robot, not necessarily the sizes and so on, everything has to be matched, but really interesting things to be done. So to conclude, essentially mixed reality, in mixed reality and AI, the key about mixed reality is that there's a ton of potential to have much more user and task context to assist the user by observing the user action, understanding the environment, accessing relevant digital information, having natural user interfaces for simplifying the interactions, and then of course being able to display information in spatial context, placing pixels wherever they are relevant. The ability to combine edge and cloud computing, the ability to have remote presence to interact with other users remotely, to be able to project your presence at a location, even physically for robotics potentially, being able to sense things remotely, get spatial context in these representations, lots of possibilities to combine HMDs, people with HMDs, with robots, with ambient sensing, IoT devices, etc. Really important in all this context and in developing this technology is to always really take privacy into account and think through the implications there. That's essentially it. Thank you. I don't know if there's still time for a few questions. I realized I took a little bit more time.
Thank you so much, Mark, for the excellent sharing. Just to share with everyone, we have 2 rooms. I know that there might be a lot of questions, but to be fair with everyone, maybe we start with room 1 for 2 questions, and then we go to the room 2 for another 2 questions. So who want to raise the first question? Oh, yes.
Hello. Thank you so much for the, is the camera from the back? Oh. Thank you so much for the presentation. It's really interesting. I'm very familiar with the HoloLens device. So that's me. I'm from a company called Innovim. We are also a Microsoft Mixed Reality partner, and we use HoloLens 2 a lot. We deploy solutions for that as well. I just would like to, I'm wondering if it's possible to have, you know, the remote presence capabilities, Microsoft Dynamics 365, for example, to be embedded into custom developed applications like from Unity, you know, to have digital twins, seeing 3D models, at the same time having, you know, remote access from Microsoft Teams, for example. So this allows you to have much richer experiences. For now, Microsoft Dynamics 365 is a standalone application. We can have our own 3D applications, digital twins, spatial computing, collaboration, and things like that. But having the capabilities of including Dynamics 365 into actual Unity applications will allow, you know, sharing of much richer experiences for various people through the Teams platform. Thank you so much.
Hey, absolutely. So I think that is, you know, I don't know exactly all the exact product timelines for some of these things and so on. But certainly the goal is to provide some of those capabilities also more broadly than just in Dynamics 365. So I know that some of those capabilities are being made available to integrate in also in third-party applications, in ISV applications, so in partner applications. Also, some of these spatial computing, these capabilities, those are also being developed. You know, we see that you know, HoloLens 2 has a lot of, you know, potential still as a device. What we see is that there's actually more these other components, exactly the ones you were mentioning, that are, you know, that we need to complete our platform to fully exploit all the capabilities. Yes, so that those things like this are definitely being planned and being developed, and will gradually become available. And so yeah, I would certainly, you know, recommend you to keep reaching out to our teams that work with partners you know, to get more detailed information there.
Okay, maybe the second question from room 1. Oh, yeah, at the back.
Hi, myself Vinu from Hanover University, Germany. So I have a specific question with respect to HoloLens and using it outdoors. Because currently when we use the device indoors, it has a position accuracy of 2 centimeters. But when we use it in an outdoor scenario, maybe based on the lighting condition, it is variable. So do you have a probable road path on this direction on using the device in outdoor scenarios in maybe probable different lighting conditions?
So for now, HoloLens, for multiple reasons, is really more focused or has been developed with indoor scenarios in mind. There's the challenges outdoors are indeed much more variable lighting. Just the amount of light that you typically have outdoors is also a challenge on the display side. There are some solutions for that, so with more opaque, you know, some sunglasses essentially for HoloLens that can now be purchased. But the reason that the tracking quality is lower outdoors is twofold. One of them is the challenge with high dynamic range. So if you have part of the space in the shadow and another one in sunlight, then the camera really can only see one of those at the same time. So it will have the exposure will only see either what's in the shadow or either what's what's in sunlight, but there's not enough dynamic range in the cameras to see both at the same time. That automatically, depending on the scenario, will create challenges for tracking. The second, so notice that the tracking doesn't use a dead camera. So the dead camera would have a challenge in too much light, too much infrared light. Indoors, that's not a problem. But if you're in full sunlight, then the depth camera would be flooded. So it can normally see even if there's ambient infrared light, but it would be flooded. The sensor would just saturate if you're in full sunlight. Notice that is actually not a problem for head tracking because the depth camera is not used for that. It is a problem for hand tracking. But then there's, so one challenge is the exposure that cannot cope with shadow and sun direction. The other challenge has to do more with the geometry of the scene. So HoloLens has a baseline between the two cameras here, about 10 centimeters. This is used for initializing maps and so on. And so when the scene is roughly at a few meters away, which has been designed for, then it works well. So if you move around a space where there's always something that's not too far away, it works very well. If you go in big open spaces where, for some period of time, there's essentially nothing in front of you or so, then the tracking quality will degrade and so on. That's part of the variability you're probably seeing. So it depends. If you move between, in small alleys and you move around there and so on, you'll probably get the same quality as indoors. But if you move in big open squares or in in areas like that where there's little to track and everything is far away, then the tracking quality, intrinsically what you track is as the visual landmarks you are tracking are further away, you will at the minimum lose linearly kind of in accuracy. If in stereo you lose quadratically, so you get some of those effects that degrade tracking quality outdoors.
Thank you.
All right,
So
maybe
in the
we
future,
turn.
definitely plan to do work there, but for now, this is where we are.
Yeah, thanks. Maybe we give the floor to the room 2. Evan, maybe you can start to look for the first question, if any.
Hello, my name is Fernando from TU Graz. Currently, the scene understanding capabilities of the HoloLens only give you planar surfaces. In your opinion, this is a limitation of hardware or algorithmic, or what plans do you think there are for improving these scene understanding capabilities?
So there's a few different things. So one is you can get meshes, which are non-planar, but then you can also indeed get planes extracted on top of that. Now there's certainly a lot of capabilities to go beyond that. You can actually yourself, with research mode, you can essentially connect the data to any 3D semantic modeling and object detection capabilities, state-of-the-art capabilities that you're interested in. That's definitely all possible. What's built in on device in real time, like available, that is currently much more limited. I think towards the future, I expect that we'll provide more capabilities over the cloud over time. But as someone mentioned, there are also their limitations in terms of, as one of the questions here, if depending on what data you want to, how rich the data is that you wanted to inference on, you have to also figure out that this is both bandwidth that you need to have available to push things to the cloud, and there might be concerns of what data does actually get uploaded to the cloud. Although, of course, we have all our documents in the cloud and all other things. So it's a question of making sure that you put it in a safe place in the cloud and that who gets access to it and so on. But yes, those are all things to be figured out. But certainly at the level of, if you are at TU Graz or in an academic setting or so on, use research mode and use whatever state-of-the-art algorithms you want to explore. And this is all possible on HoloLens. by just going yourself for sensor access and exploring exactly the object detections, the semantics, all of the things you're particularly interested in your applications. You should be able to do all of this.
Thank you.
Is there any other question from room 2? If no, I think that we have also around 100 persons online. So I think that, okay, so maybe it's also good for us to give them a chance. So Mark, if you don't mind, I just, just randomly select, do the time. So I just randomly select some questions for you. It's okay? Another 2 questions?
Mm-hmm.
Yeah. So the first question is from Gabriel Soros. I hope that I pronounce your name correctly. So this is about Azure. So the question is, Azure anchors require the user to upload image or maps of the factory to the cloud, which might be sensitive, even with the line cloud approach. Is it possible to host the anchor service locally in a private 5G network?
So in the current product instance here, so first, we don't upload images, but we just upload limited feature descriptors and so on. And of course, this is all, the data is owned by the company. So it's not that you upload this to a public representation that everybody gets access to. It is, if a company sets this up for themselves, then of course this is their data. And so, as I was saying before, if it's their they put their documents in the cloud, they also put this data in the cloud. This is owned by the company. So in the industrial setting, this is typically not necessarily a concern. Now, there can still be some concerns. Certainly in some scenarios, the technology should enable to also, of course, work with an on-prem capabilities, or there certainly things can be developed. This is not the current service. Azure Spatial Anchors is hosted in the cloud. Technologically, we could of course also make it possible, enable it on premise and so on. But that causes other challenges then. But yes, so this is all possible, and depending on what's needed and the feedback from customers and so on, we'll make sure to shape things in the right in the way that makes sense to our customers.
This is the last question from Jingwen Dai. Yes. So I guess Mark, you also know him. So the question is, could you please give more details of recording MR assistant content using the time of flight sensor? I think this is a big question. More details about more details of recording MR assistant content using the TOF sensor.
Yeah. So let's see. So reading question here. So for now, when it gets streamed, so when like in the product, if you do remote assistance and you use that, it does actually leverage the depth camera, because it allows remote people to place instructions on the actual scene in 3D. So if you wanted to communicate to a person, a remote person wants to indicate press that button, you can actually put an arrow in 3D on top of that button, and that leverages the depth camera. So it intersects essentially the pixel clicked by the person remotely. It intersects that with the actual depth and places at that location the instruction, so that if the person on site moves around, the instruction, the arrow is actually stabilized in 3D. At that particular 3D location. So it does use that. Now for doing that, it doesn't actually have to stream like the whole 3D all the time or so, and so on. So for now, this is limited. I expect that in the future. So for example, in our project with the hospitals here in Switzerland, in terms of the AR, VR, surgical education, medical education project, There, we certainly intend to have the full 4D streaming of the content plus annotations on top of it be streamed, like the full, visual 3-dimensional, 4-dimensional content essentially to be streamed. So I think for now it's more limited, but certainly down the road we expect that to be much more richer representations being streamed. Also, some of the real life avatar capture is actually also based on Azure Kinect. And is kind of essentially 4D or 2.5D kind of plus time streaming, etc. So some of that is certainly there, yes.
All right, thank you so much, Mark. So maybe let's give another applause for the keynote by Professor Mark Poloface. Yeah.
Thank you.
So I hope that you can come to Singapore in person one day and we can meet again. Thank you so much. Have a nice day. Yeah.
Bye-bye.
Okay, bye-bye. All right. I think that due to the time schedule of today's program, we have a banquet dinner. So the next session, maybe just start immediately. Thank you so much again. Thank you.
Hello everyone. Welcome to the Social Issues, Behavior and Empathy paper track. I, Kunal Gupta from Empathic Computing Lab at University of Auckland, will be facilitating this session. So I think everyone would be excited for the banquet, so we'll just start the session. And I invite Adrian Verhulst, I hope I pronounce your name correctly, to talk about their paper titled Parallel Adaptation. Switching between two virtual bodies with different perspectives enables dual motor adaptation. Floor is yours.
Okay. Hi. So yeah, this work is about parallel adaptation, but our goal is to study dual embodiment. So dual embodiment is the possibility to be embodied into two bodies at the same time, like single embodiment, but in two bodies. The way we do it is that we are going to switch between two bodies. So you start, for example, in body A, the red one, and then after a few seconds, you switch to the other body. And then after a few seconds, you switch back to the red body, okay? And you do that again and again and again. So the issue is that if the bodies are somewhat different, like here, a tall one and a small one, and if you try to do a single thing, like reaching an object, with one body, you will have a long arm, and therefore you don't need to reach as far as usual. But with the other body, you have a smaller arm, and you need to reach further away for the same target. It means that you need, for the same movement, reaching a target, you need to have two ways to do it. And you need to switch between those two ways. So we call that internal model, which is simply put a way to think about your motion while you are doing it and before as well. So you need to have two internal models, one for each body. And also you need to be able to easily switch between those two models. Because we don't want, like, for example, let's say I'm inside the red body. We don't want to think, oh, I'm inside, I see the background, therefore I'm inside the red body, therefore I am taller, therefore I need to reach further away, and I do the motion. We don't want that. We just want, oh, I'm inside the body, I reach a target. So we need to switch between our internal model very easily. And in those two conditions, we believe that we can get dual embodiment. So in our task, our two virtual bodies will be the same, okay? But we still need to provide some difference so the user can develop two internal models. It will be done by having a perturbation between the two bodies, a rotation, simply put. So let's say that my real motion is like that. I'm going to have a rotation offset for one virtual body up. So the virtual body will go in that direction. And for the other virtual body, I will have an opposite rotation. So if I do my real motion like that, the other body will go like that. Okay? And I switch constantly between those two rotations. So of course it's difficult. There is two ways to adapt to those two different perturbations, explicitly and implicitly. So in explicit adaptation, it means that I need to think about it. I need to think, if I want to reach a target here, I need to think, I'm inside a red body that has a rotation like that. So to reach a target here, I need to do my real motion like that. Therefore, the virtual body will reach the target here. Okay? And you need to think that, you need to strategize your motion every time you switch body. It's difficult, but it's done explicitly. You think about it. In implicit adaptation, you're not going to think about it. It's just going to happen over time. Of course, what we'd like to have is implicit adaptation because, again, we want to switch internal model without thinking too much about it. So let's talk about the experiment now. So the task itself here is very simple. You have a target, the red cylinder, the green cylinder. You reach it, you go back to the start position. You reach it, you go back to the start position, and so on. Very simple. Because we have two VR body with perturbation, so you will have a lot of trials here, the number of trials. And the perturbation is going to start at 0, then increase over trial. At 15 degrees, it reaches the maximum. It stays at 15 degrees, and then it goes back to 0. And for the other body, we got the opposite perturbation. Okay? So we have 4 conditions based on 2 independent variables, the perspective and head rotation. So why did we choose those independent variables? We still need to provide to the user a cue that is inside one body or another body. So to do it, we can decide to change the background. Like one body is inside a forest, another body is inside an office. Okay? But the issue is that the user is very focused on the task and is not going to notice the background. So we need to provide better context cues. And that's why we decided to focus on perspective and head rotation. So let me present the condition. This one is first-person view and no head rotation. Okay? You can see that you switch body when the background changes. This one, first-person view, but you need to rotate the head. In one body, you need to rotate the head to the left to see the target. In the other body, you start in that direction. You need to rotate the head to the right to see the target. This one, third-person view, you don't need to rotate the head. You see, when you switch, the target is in view. This one, third-person perspective, but you need to rotate the head, the most difficult one. So now the results. So that's, this one is the result for one first-person view, no need to rotate the head. Okay? In blue here, you have the perturbation over trial. Okay, so it's, let me go back, it's this one, okay, but in blue. In red and green, you have the direction error. So the direction error is an angle error. So let's say that you need to reach, you start here, you need to reach that point. Okay, so you need to do a motion like that. But there is a perturbation, and the perturbation will make your motion go in the wrong direction. You realize it's in the wrong direction, and you correct it, meaning that your path will be like that. So you need to go like that, but you do a path like that, and that is your angle error, or direction error. Of course, if you have a direction error of 0, it means that you did the motion perfectly. So at the beginning, there is no perturbation. So let's check for the red body, okay? No perturbation, and then the perturbation increases, as well as the direction error. So that's one thing. The second thing is that when the perturbation stays at 15 degrees, the direction error doesn't decrease. another thing. And third is that when you remove the perturbation, the direction error goes back to 0 right away. And those three elements, so a lot of error, the error doesn't decrease and goes back to 0 when you remove the perturbation. Those three elements are signs of explicit adaptation. It means that the user strategizes. It means that every time there was a switch of body, he thought about it. Okay. Those results are for third-person perspective. We group them together because no head rotation and head rotation. We put them together because they are kind of similar. But let's focus on third-person no head rotation. It's very different. First, the adaptation, the direction error doesn't increase as much. Okay, it doesn't go to the max, and then over time it decreases. And when you remove the perturbation, here you can see that it's not going to go back directly to the to no direction error. It's going to take a few trials. So that is a sign of implicit adaptation. It means that when the user did the task, he didn't realize maybe didn't realize there was a perturbation, and even if he did, he didn't know by how much he corrected his motion. So of course, when you remove the perturbation, the user is just going to be like, it's weird, I cannot do my motion anymore, like I'm not reaching the target anymore. But he doesn't know how to correct it. So it's going to take time and trials to go back to no direction error. And we have that kind of exponential decay function here. Okay? So that's implicit adaptation. It also happened for 3pp and head rotation, but a little bit more. We don't really have that decrease here, but we still have that nice exponential decay, as well as a low adaptation. Direction error. So what does it mean? It means that what we managed to do here is that in a specific case, so in third-person view, when you need to adapt to two different bodies at the same time, we believe, we know that the user is able to adapt better. Okay, that's one thing. So we think that he's able to adapt better because he developed two body internal models. And that is one thing that we want for dual embodiment. We think that it's just going to adapt better because there is one body model for each body. The other thing is that when we did the experiment, the users, the participants didn't really notice there was a perturbation. Like even when there was a 15-degree rotation, they didn't notice there was a perturbation, meaning that they're able to switch body and to still do a correct motion without thinking about it. And that's also what we want for dual adaptation. We got those two elements. Maybe we got, for each virtual body, one body model, and also we get a switching of body model without the user thinking about it. And that brings us closer to dual adaptation. Inside the paper, we also compared the body ownership, agency, and workload. So please check it out. That will be all for me, I think. Oh, and if you want to try the demonstration, we will be at SIGGRAPH Asia in Korea in a few months. And if you are here, please come and you can check it out. Thank you.
Great. Thank you, Adrian. So I think we have time for one short question. Anyone? Anyone? No? So mainly I just wanted to understand if you compared any comfort level when they were switching the bodies or something like that. Mm-hmm. So did you have any insights on that?
When we switch the body, you mean? How does it happen?
Yeah, when they were switching the automatic adaptation.
So the switching body, how it happened is you just, you have a video right here.
Yeah.
It's going to happen randomly, by the way. The user, it doesn't happen every time.
Okay.
And that's pretty much it. Something important to say, I mean, again, that condition is the perspective condition. It's very important that we provide context cues for the user so he's able to know in which body he is. And you can see that the camera position, wait, okay, you cannot see, but the camera position, okay, good. The camera position is not in the same direction, okay? Because if we put them in the same direction, again, we have the same issue than first-person perspective. The user needs to focus on the background instead of just looking at it and knowing. I hope it's okay.
Thank you.
Thank you.
Thank you. Yeah, I think we can start the next. Okay. Yeah, thank you very much. Next, I invite Taiki Kodama to present their research on enhancing the sense of agency by transitional weight control in virtual co-embodiment.
Thank you for the introduction. Hello everyone, I am Daiki Kodama from the University of Tokyo. It is a great honor to be able to speak to you today. From now on, I'd like to introduce our work on the following topic, enhancing the sense of agency by transitional weight control in virtual co-embodiment. First of all, an overview of the research. We propose to transitionally manipulate the control weight in virtual co-embodiment and show that transient weight manipulation could improve the sense of agency, which may lead to more efficient motor skill transfer. And the research background is that the transitional method of motor skill transfer is not efficient. Observing a teacher's movements from a third-person perspective is a typical method of motor skill transfer. Although such method is widely adopted in a real environment, it is likely to induce numerous errors in the cognitive process of converting movements observed in the teacher's body coordinates to those of the learner. Virtual reality systems have been developed to solve this problem by superimposing a teacher's movement as a translucent avatar on the learner's first-person perspective. Because the learner can omit the body transform coordination in this system, they can reproduce the teacher's movements better. However, there is a problem that this system has a problem with the long-term retention of skills. This problem is due to a weak sense of agency, the feeling of initiating and controlling an action because of distraction from following the teacher's movements. Virtual co-embodiment has the potential to address this issue. In virtual co-embodiment, a virtual avatar is controlled based on the weighted average of the movements of multiple entities. It is known that a user feels a strong sense of agency towards the movements that they did not cause. Arising a strong sense of agency is important for motor skill transfer. The mechanism of motor skill transfer in virtual co-embodiment is as follows. In this system, a teacher and a learner share the avatar and perform the motor skill. The teacher perceives errors caused by the learner and corrects them so that the co-embodied avatar moves correctly. On the other hand, the learner understands the correct movement caused by the teacher from the first-person perspective. If the learner can feel a strong sense of agency in the co-embodied avatar, they can acquire the skill as their own. However, when using static weights, there is a trade-off between the sense of agency and ease of understanding the teacher's movements. In virtual co-embodiment, the learner's control weight should increase to induce a strong sense of agency. However, this means that the teacher's control weight decreases, making it challenging to understand accurate movements through the avatar. Because the previous studies on virtual co-embodiment only measure the degree of sense of agency induced at a particular control weight, there's a research gap in the design of control weights to induce a strong sense of agency and overcome this trade-off. To resolve this trade-off, we focus on the two-step account of agency model, which explains the mechanism of arising sense of agency. A sense of agency is induced when the prediction of the outcome of the action is consistent with actually sensory feedback. Furthermore, according to this model, a sense of agency is also influenced by posteriori reasoning that considers beliefs and context. Then, we focus on the context and propose traditional weight control. Specifically, we suggest that the initial weight high and then lowering it gradually. We hypothesize that by creating a context in which a strong sense of agency was generated, the sense of agency after decreasing the weight, like here, would become stronger. We experiment with investigating this hypothesis. In this experiment, we implemented the irritating maze task. These videos are the user playing the irritating maze task. Participants carried a stick from the start to the goal point without hitting the course frame or moving obstacles in this task. The task had a single path where participants could easily anticipate their directions. The task consisted of two courses: the introduction, shown in the video on the left, and the main course, shown in the video on the right. To control the participants' movements, we specify the speed of the task. In addition, to control the collaborative partners' movements, we embodied the participants with a log of the correct movements using time step. The participants were told to share the avatar with the experimenter in front of them because the sense of agency is affected by whether the participants believe that a collaborative partner is a person or a mechanical trajectory. The experiment was conducted using within subject design. The control method and weight in the main task were independent variables. The control method refers to how the control weight changes in the introduction task. In the static condition, the weights in the introduction task were always the same as those in the main task. On the other hand, in the traditional condition, the participants started the introduction task with 100% weight, and the control weight was linearly decreased to the weight in the main task at the end of the introduction task. As for the weight in the main task, we set 4 conditions: 0, 25, 50, and 75%. In addition, there was a static 100 condition where participants' movements were fully reflected as a control condition. The sense of agency in the main task was assessed using a questionnaire based on previous work. The contents of the questionnaire was in the right figure. Participants answered each question on a 7-point Likert scale. The average was used after inverting the score equal 8- score for Q3, Q4, Q5, Q10, and Q11. We hypothesized that participants under the transitional condition would have a stronger sense of agency than those in the static condition. Here are the results showing the sense of agency. Because the Likert scale is ordinal, an aligned rank transform was applied to each data. Two-way ANOVAs with the within subject factors were performed for the sense of agency. As a result, the main effect of control method was significant, which means that the sense of agency in the transitional condition is significantly stronger than that in the static condition. The main effect of weight was also significant. The post-hoc analysis shows that the sense of agency was stronger in the order of 75%, 50%, 25%, and 0%. The interaction between the control method and weight was not significant. As hypothesized, the proposed method strengthens the sense of agency. Here, we can consider two possible reasons: the experience of high weight and the gradual weight change. As for the experience of high weight, the primacy effect may have a significant influence. The primacy effect is the effect that the first experiment significantly influences the overall experience. The participants' comments support this. There were some conditions that I thought my weight was high at first. Therefore, it may be important to feel the strong sense of agency at the beginning. As for gradual weight change, some research implies the importance of gradual weight change. For example, it is reported that the more gradual the change in the feedback on one's actions, the less likely the user notices the change. Therefore, we'll discuss how important it is to feel that there was no change in weight from the participants' comment. The post-experiment questionnaire shows that 23 of 24 participants mentioned weight change, like there was a condition in which I could move entirely at first, and then I was unable to move at all in the end. This result means that most participants noticed the weight change. On the other hand, even in the transitional zero condition, which was the easiest to notice changes, it seems to have improved the sense of agency. Therefore, the experience of high weight in the beginning may be more critical than not noticing the weight change. In future work, we will identify the factors to improve the sense of agency. For example, we will add a step function, which is considered easy to notice, or logarithmic condition, which is considered hard to notice, and evaluate the sense of agency. In addition, as future work, we consider applying transitional weight control to motor skill transfer. To take advantage of transitional control, we'll select skills that require different proficiencies at different timing, such as golf or batting in baseball. By increasing the runner's weight when advanced skill is not required, a strong sense of agency might arise. Finally, this is a summary of our study. We proposed enhancing sense of agency by transitional weight control based on two-step account of agency models. Our results showed a stronger sense of agency and considered two possible reasons for this: the experience of a high weight in the beginning and the gradual weight change. In future work, we will identify the factors to improve sense of agency or apply this method to motor skill transfer. That's all. Thank you very much for your attention.
Thanks, Delphi. Do we have any question?
Hi, thank you for the lovely study. My name's Ife. I'm a PhD student at Carnegie Mellon University. So you mentioned that the co-embodied avatar followed a correct trajectory. I'm wondering if you had any thoughts on, like, what exactly the other avatar was doing may influence the results for, like, if you had an avatar that followed maybe an intentionally incorrect trajectory, if that would play a role in how that would factor into the user experience.
Maybe I think that in this experiment, we use the trajectory, but when we apply this to motor skills, we will use teacher to modify the incorrect movement of the learner. Then this result is because cannot apply to the teacher, not trajectory, but we can think that. I'm sorry. Could you ask me again?
So in the study, it seems like the teacher was following the correct trajectory. Like obviously as a teacher, you won't be following an incorrect trajectory, but I was just wondering if you had any intuition about if that would influence your results. Like if there was someone that, I mean, I was thinking about other use cases where if you had two users co-embody the same avatar, the likelihood is not both users will be perfect at the task, right? So I'm wondering if you had an intuition for, you know, what are the sense of agency or sense of presence effects of potentially dealing with something that's adversarial.
Yes,
or like, yeah, they're not doing whoever you're sharing that body with is not doing the right thing. I wonder if you have any thoughts about if that would influence your results.
In this regards, that it's, in my opinion, that teachers' motor intention will convey to the learner, and then first they move separately. The teacher and the learner move differently, but as the time goes and practice more times, they will move the same. Then they can feel the strong sense of agency, or we can apply to motor skill, we think. Is it can I answer you?
We should chat afterwards, but thank you so much.
Yeah, thanks, Daiki.
Thank you.
Thanks, Daiki. Yeah. You can talk over the dinner, yeah. Yeah, I think the time's up, so we can invite the other person. Thank you very much, Daiki, for your presentation.
Thank
you. So next I invite Hyungil Nam. He'll be presenting his research on an emotionally responsive virtual parent for pediatric nursing education, a framework for multimodal, momentary, and accumulated interventions.
Yes. Hello, I'm Hyungil Nam from Hanyang University. I'm going to talk about our paper on emotionally response virtual parent for pediatric nursing education, and which was collaborated with nursing faculty. For quality healthcare service, it is important to improve not only patient experience, but also family experience. In pediatric nursing, social skills and communication with patient parents are especially important. So, when being on clinical nursing training, the pediatric nurses need to grow emotional intelligence, not only clinical knowledge. In previous research, there have been many VR-based nursing education and training applications which were proved to be effective. Even there are several commercial applications for training students and professional nurses. But In the context of pediatric nursing, there is still lack of training examples which can provide realistic parent reactions. So our research is about multimodal nursing intervention analysis framework for updating virtual parent emotion. Also, we present a realistic pediatric nursing scenario in VR developed together with nursing faculties and professional nurses evaluate our system and the scenario. First, I will describe our framework that analyzes nursing interventions and provides possible parent emotions. This is the entire framework. The overall process is like this. The framework analyzes users' momentary intervention and accumulated nursing intervention, which is evaluated and converted to emotional impact. And the current emotion will be updated based on emotional impact. This sounds so complicated, but I will explain step by step from now on. First, I will talk about momentary intervention analysis part. The part analyzes both verbal and non-verbal behavior inputs. For verbal inputs, the framework evaluates spoken words in two aspects: clinical information and emotional supports. About non-verbal analysis, our framework analyzes the use of virtual nursing tools, how the user grabs and use them with hand gestures and postures in VR. Non-verbal components would be associated with these sophisticated skills, such as a speed of the hand pose, and procedural order in the use of nursing tools. Next, I will talk about accumulated nursing intervention part. For example, the intervention of removing injection process include not only the removal process, but also how to use alcohol swab or how to use medical devices attached to the patient. So we estimate what the current intervention is by analyzing multiple momentary inputs, actually momentary actions. For this, we tokenize and analyze verbal and non-verbal behaviors to classify the intervention using KNN method in real time. Then with the estimated intervention, our framework will evaluate whether the user performs what they are supposed to do. And finally, the evaluated results will be converted into nursing performance index, positive, neutral, and negative. Now, the nursing performance indices are mapped to 5 elements of emotion impact factors: happiness, satisfaction, neutrality, anxiety, and anger. And now, the framework can calculate potential emotion. This is an example. You may see details on our paper. I will describe some of the important points. Every person has a different personality, and they can differently feel the emotion impact depending on their personality. So we consider personality to define the emotional sensitivity. Also, to consider reinforcement effect. When the same emotion impact appears repeatedly, the virtual parent would feel the emotion more strongly. On the other hand, if current emotion factor element does not change, the emotion will fade away, which is attenuation effect. And now the framework can update current emotion state based on the calculated potential emotion and trust that the patient may have towards the nurse. And in the updated emotion vector, the highest elements will be chosen to decide the parent's dominant emotion. Okay, with our framework, we made a realistic pediatric nursing scenario and developed our VR system with virtual parent. As you can see, we designed momentary and accumulated nursing intervention and developed virtual parents' dynamic emotional reactions. And we made a patient discharge scenario with a child patient in the pneumonia, which include 7 major interventions. I will show you a short video clip. This is a little exaggerated to show emotional changes during intravenous injection remover. Current state is angry, and there is no any other emotion values. And slide it. In the slide. Oh. How can I use that? Okay, the video has some trouble. Oh, there is some trouble in video, but I will say then my presentation keep going. Yeah, the user performs momentary interventions in the video. When the virtual parents get angry, the users gave the neutral emotion impacts to child patient in multiple times, such as pushing the button or using alcohol swabs. These behaviors make the virtual parent emotion neutral. After that, the later video, the users remove the injection slowly while using both hands holding the child arms, and the child's skin is too sensitive and weak, so pediatric nurse should remove injection carefully. This behavior make positive emotion impact, and the users comment for also emotionally support positive impact to the virtual parents. With these actions, the virtual parents would be satisfied and react positively. Finally, professional nurses evaluated our developed system for feasibility. We used a within subject design with 10 participants, and we removed one because of some technical issues. They experienced static and dynamic emotion of virtual parent. In the static condition, the parent only expressed neutral emotion, while she had 5 different emotions in dynamic condition. we measured both objective intervention, estimation, accuracy, and subjective perception, immersion, realism, learning efficacy, and usefulness. For immersion, realism, and learning efficacy, we asked them about both verbal and non-verbal interactions. And for usefulness, we want to know this framework can be applied in actual pediatric nursing education. Like this. First, we confirmed that our framework could estimate nursing intervention accurately. Overall, out of a total of 50 nursing intervention estimates, 45 accumulated nursing intervention estimation were successful. Also, the results of our subjective perception measures show that dynamic condition was significantly better than the static condition in terms of realism, learning efficacy, and usefulness. In summary, we developed a novel nursing intervention analysis framework for nursing education. We proved the potential of our framework as an educational tool that can provide realistic first-hand experience and usefulness. But participants reported some limitations. In some cases, when the speech recognizer was delayed or difficult to perform, participants felt inconvenient. Also, they sometimes felt fatigued to unfamiliar VR environment for a long-time experiment. They particularly mentioned that they want to see a diverse intervention scenarios. Based on these comments, we plan to include different modality inputs and outputs in our framework and extend the intervention scenario in different contexts. Thank you for listening.
Thank you, Helga. We have time for maybe one quick question. Anyone? No? Okay. Then maybe we can, if anyone has any question, we can ask. You can ask him later, maybe. Thank you. Thank you very much. So next I'm inviting Benjamin Freeling to talk about his research on petting a cat helps you incarnate the avatar, influence on the emotions over embodiment in virtual reality.
Hi, thank you very much. Thanks for coming to this presentation, where I will talk about the influence of emotions over embodiment in virtual reality. My name is Benjamin Freeling, and I'm a first-year PhD student. I'm here with my co-worker and supervisor, Flavien Lécuyer from Strasbourg University in France. As you all know, virtual reality is a strong tool in many fields, mainly because of its capacity to elicit a strong sense of self-representation. This is due from the feeling of presence, the feeling of being physically and spatially located in an environment, and the sense of embodiment, the feeling of possessing the virtual body called avatar as our own. The embodiment is particularly important as it links the user with the virtual body he possesses during the virtual reality experiment. Another advantage of virtual reality is the emotional implication it allows, which is crucial for applications such as medical therapy or entertainment. So what's the relation between emotions and embodiment, and has been studied before? Sense of presence has shown correlation with emotions by Lemens and colleagues in 2021 and with embodiment by Riva and colleagues in 2007. But the relationship between emotions and embodiment has never been studied before. Concerning emotions in virtual reality, we can see from Luong and colleagues in their state-of-the-art in 2021, and for example, in Dewez and colleagues' experiment on embodiment in 2019, that most studies on emotions, or particularly on embodiment, were acquired through negative stimuli with negative emotions used as indicators for embodiment. In our case, we are trying to study the impact of emotions over embodiment, and for the purpose of medical therapy, where negative emotions could be counterproductive, we have decided to research the effects of positive and negative emotions over embodiment. At this end, we've created an experiment with 3 hypotheses. First, our environment will succeed at eliciting emotions, positive and negative. With the avatar that we will use, we will see that more realistic avatars generate stronger levels of embodiment. Those 2 hypotheses will validate our environment and will allow the last one, which is eliciting a stronger emotion generates a stronger sense of embodiment. To answer those, we have put together an experimental setup, starting with the environment. It represents a simple office with 3 desks, placed with a similar layout as the real room the experiment took place. The users sit at the front desk. They are corresponding placed in the real room, and a mirror is placed on the wall in front of them so they can see their reflection. As our environment didn't require any input button from the users, we choose not to use the controllers in favor of trackers, allowing the user to use their hands as the avatar would. So for this purpose, everything is collocated and at scale with the real world. We choose to reproduce the same office to provide an environment as familiar and emotionally neutral as possible. To create emotion, we manage 3 conditions. A positive emotion coming from a cat, jumping on the desk to be pet and purring stronger as we do so. The haptic feedback is given by a cat plush placed on the desk as best as we could. We created a neutral emotive condition with a simple quiz consisting of geometrical questions to keep the users mentally active in the scene to avoid boredom. To avert positive or negative emotions during the quiz, results aren't given and there's no time limit. Haptic feedback is here given by real buzzers on the desk that users can press on. Last emotional condition is the negative one, elicited here by a box of swarming insects such as cockroaches, ants, worms, and a big spider in the corner of the box. The task here for the users was to dip their hands in the box, which was also placed in a real world, full of plastic insects and a spider plush. And all of that while a swarming insect sounds was playing in their ears. Our avatars were mainly divided in 2 axes, completeness and realism. We have the partial abstract avatar, which is only 2 gray spheres replacing hands, and the partial real with 2 human hands. For the full body avatars, we have adjusted the virtual body to correspond the gender of the participant, as there was more body part to see. So the abstract one is a robot or a dummy, and the height corresponds to the mean height of French men and women. Last are the real ones, representing a man in a suit and woman in jean t-shirts with measurements same as before. To evaluate the emotional responses, we used subjective measurements, such as the self-assessment mannequin, known as SAM, here on the right, where each line corresponds to a component of emotional state: arousal, dominance, and valence. Users are asked to pick one mannequin on each line, corresponding or symbolizing best the emotional states they were during the experiment. For the embodiment measurement, we used the standardized avatar embodiment questionnaire from Peck and colleagues in 2021, where they have decomposed embodiment into 5 subcomponents, such as appearance, the appearance of the avatar; response, which is the bidirectional relation between the avatar and the environment; ownership, the feeling of owning the virtual body; multisensory, the consistency between senses; and agency, the capacity to control the avatar. To evaluate the environment and the sickness, we used the Sickness Simulator Questionnaire from Canadian colleagues in 1993 and the Presence Questionnaire from Whitmer and colleague in 2005. For the protocol, we start with the presentation of the experiment, the consent and the sociological questionnaire. We then ask the SSQ and to see if the user was apt to go to VR. And after that, they had 6 conditions. A condition being a couple avatar with an emotion and is chosen through a Latin square. Each condition lasts 3 minutes, 1 to discover the avatar and the interaction with the world, and then 2 minutes of emotional stimulus. The SAM and embodiment questionnaires are asked between each condition, and the SSQ and present questionnaire are asked at the end. The experiment took place in May and gathered 30 participants, aged from 18 to 58, with a mean of 26.3. Their use of virtual reality differs, but most of them were rarely users. From the data we gathered, we conducted several statistical tests, which gave the following results. The objective was to verify that our experimental setup gave the expected results in terms of emotional induction to validate our first hypothesis. We can see that the cat and insect condition, on the first one in the arousal, on the left, we can see that the cat and insect conditions generate a significant higher arousal than the neutral condition. We see that there is not a significant difference between positive and negative stimulus, and that the insect condition has its arousal quite scattered. For the valence, negative stimulus is still scattered. Yes, that means that some had fun with swarming insects. I don't know. But there is a significant difference between each emotional condition. Those results confirms that the stimuli was able to generate contradictory emotions on participants, with the cat condition being significantly more positive than insects and neutral. This then supports our first hypothesis. Now, what about the avatar's condition on embodiment? Without any surprise, we can see that the sense of embodiment grows with the completeness and the realism of the avatar, this difference being significant between the partial abstract one with the 2 spheres and the others. Our experimental setup is able to generate different levels of embodiment from levels of avatar completeness and realism, which support our second hypothesis. Concerning the influence of emotions, the result suggests that emotions have a significant positive influence over embodiment. We can see here that embodiment is stronger when an emotion induction stimulus appears in virtual reality, whether it be positive or negative stimulus. The graphic on the right shows that overall embodiment is strongly linked with the arousal aspect of the emotion, and that the main components impacted are response and appearance, thus supporting our third hypothesis. To conclude, we've seen that eliciting a stronger emotion generates a stronger sense of embodiment, but the emotion induction stimulus is a key factor to get the best results. For example, we noticed mitigated results for the insect condition because the negative feeling wasn't as strong as we expected. This contribution shows that in virtual reality, emotion stimuli is a key to user implication. It creates new perspective in medical therapy and entertainment, as a simple emotion stimuli can make users more engaged in the virtual environment presented to them. In the future, we would like to study other aspects of embodiment, like agency, as user feedback mainly pointed at the lack of finger control they had during the experiment, as we used hand trackers. And to complete our study, we would like to investigate the physiological data we gathered during the experiment to complement the subjective emotion evaluation with objective data. Thank you very much for your attention.
Thank you, Benjamin. Any questions? We can have one quick question. No? I have a question. So, when you were conducting the experiment, I assume the insects condition would be like somewhat fearful or scary for the participants. So, did you get any insights on like the verbal communication that like the experience that they were having while like emotional experience or something?
Some of them did, but as we can see in the results, some of them didn't, as they were not as scared as insects as we thought. So, yeah. When we asked the question, how do you like insects? Between the scale, -5 is I hate them, and 5 is I love them. The mean answer for that question for insects was like -1, so they were not as scared as we thought.
Interesting. Thank you.
Thank you very much.
No other question? Okay. Thank you, Benjamin. Yeah. Next, I invite Chen Li to talk about their research on use virtual reality to enhance intercultural sensitivity, a randomized parallel longitudinal study, and it's a TVCG paper. Please welcome Chen Li.
Hello, good afternoon. I'm Chen Li Richard from the Hong Kong Polytechnic University. On behalf of my co-authors, Ms. Angel Kong and Professor Horace Yip from City University of Hong Kong, I'm going to present this journal track paper, Use Virtual Reality to Enhance Intercultural Sensitivity, a randomized parallel longitudinal study. As you may see that the title actually tells you a lot of story. It tells you the objective of this particular project, as well as the method we took. But don't worry, I will talk about all these little details later on. So I will start by looking into the backgrounds and also theoretical foundation. So first of all, as we are going to use virtual reality to enhance people's intercultural sensitivity, we start by looking into the definition of intercultural sensitivity because it is constantly evolving. And we found that the most accepted definition of intercultural sensitivity has a clear emphasis on the human emotion. And on the other hand, just as Benjamin has just mentioned, presence and embodiment, they both have a very close relation to emotional reactivity of the participants. So suppose that the sense of presence is related to emotional reactivity and intercultural sensitivity is also related to human emotions. Can the sense of presence experienced during VR exposure lead to the enhancement of intercultural sensitivity? This is the question we wish to know. To formalize this study, we proposed 5 different research questions. So the first research question is, can the intercultural sensitivity of the VR group be enhanced immediately after the exposure? And for research question number 2, we really wish to know, can the enhancement of the intercultural sensitivity of the VR group be retained 3 weeks after the exposure? I think you have the sense that why we need to conduct a longitudinal study. And both these 2 research questions tries to look into the within subject group, within subject effects. And we also have research questions 3 and 4. These 2 are for the between subject effects. We really wish to compare VR with other modalities. So for example, video and also, of course, control. The last research question number 5, is about what are the predictive factors of the change in the intercultural sensitivity of the VR group. This is a super important question because even for us, we don't know what are the factors that can contribute to the positive effects we wish to see. So developing all these VR scenarios could be quite expensive, and it's basically a trial and error process. So if we can identify all these factors, then basically we can make this design process more cost effective. Of course, it is not possible to just invest all potential factors. So in this particular paper, based on our theoretical foundation, we focus on 2 factors. The first one would be the participants' emotional empathy. Okay, so we do have a very strong support regarding the human emotions in the process of training intercultural sensitivity. And the other one would be the sense of presence. Okay, so this is the core of any VR experience. So next, I move on to the experimental design. We conduct this three-group randomized parallel longitudinal study. We have three groups: VR group, video group, and control group, as I mentioned. And we have three key time points. T1 is 1 week before the exposure, and T2 is right after the exposure, and T3 is 3 weeks after exposure. So all the measurements were taken at these three key time points, and you can consider the measurements taken at T1 as the baseline. So it helps us to mitigate any kinds of potential bias or imbalance among the participants in addition to the randomization process. And for T2, you can consider this as a measurement for the immediate effects, and for T3 is the measurement for the retained effects. So these are the participants. Initially, we recruited a total of 90 participants, but due to various reasons, COVID and time constraints, in the end, we only included 80 participants in the analysis. So I won't dive into the details, but I just want to point out two things. So the first thing is that, as you may see from the figures, we have a slight gender imbalance among all the participants. We have slightly more female participants. And the second thing I wish to point out is the definition of ethnic minorities in Hong Kong. Okay, so this may vary, depends on the region you are talking about this concept. But in Hong Kong, we follow the government's definition of ethnic minority. That is the non-Chinese. Okay, so anyone non-Chinese will be considered as ethnic minority in our study. So for the materials, we basically used the VR scenarios we made for these for the VR group, and also the converted videos for the video group. So we made 3 VR scenarios based on the 3 typical locations reflecting the daily lives of ethnic minorities in Hong Kong. So the 3 locations were associated with 3 different topics. So this one is about family and history. The second one is about the religious beliefs and identity. I guess if you've ever been to Hong Kong, you will immediately identify this picture. It's the Kowloon Mosque, okay, in Hong Kong. And the last one is about the communal life in Hong Kong. Okay, we have another paper, IEEE VR poster last year, talking about how we made these, very nice scenarios using reconstruction method. So if you are interested, you can go to and check it out. Yeah, and also we use the gamification techniques, okay, in the to design the interactions. So we embed some discoverable spots and the locations items in the scenarios, like a classical puzzle game. So the participants needed to navigate in the scenario, and once they are very close to the spot and items, these kind of visual cues will light up, and they can to help them and give them a hint that they can interact with the items and also learn some intercultural knowledge. Next, we move on to the measures. We basically rely on well-validated instruments to do these measures. So to measure intercultural sensitivity at T1, T2, and T3, we use the intercultural sensitivity scale. For emotional empathy at T1, because it's a trait, so we only need to measure it once, we used the empathic concern subscale of the interpersonal reactivity index. And for the presence at T2, for the VR group only, of course, we use the IPQ scale. I guess you are all very familiar with this. For the last one, the intercultural knowledge at T1, T2, and T3, we used a self-developed intercultural knowledge test. So it contains a total number of 9 multiple choice questions. So the maximum score would be 9, and the minimal score would be 0. So here are the results, the descriptive statistics. As you can see, we measured ISS, intercultural sensitivity using ISS across 3 different time points across 3 groups. And the ISS score and the IKT score were analyzed using mixed ANOVA followed by pairwise comparison with a Bufferoni adjustment. For the empathic concern and IPQ scores, we actually used them as the independent variable for the hierarchical multilinear regression, okay, to answer basically research question number 5. So I will talk about this later. Okay, so here are the results. So for the research question number 1 and number 2, as I mentioned, they are all looking into the within subject effects. So although the figure may look a little bit cluttered, you only need to look at these red dots because they are representing for the VR group. So in the pairwise comparison, we found that compared to T1, the difference between T1 and T2 in terms of the ISS score is significant. Okay, the difference between T1 and T3 is also significant, and the difference between T2 and T3 is not that significant. So it is very safe to say that VR is very effective in enhancing intercultural sensitivity, and also this kind of enhancement can be retained for at least 3 weeks. Next, we look into the research question number 3 and number 4. So these are the between subject effects. Okay. So for T1, we did some. We also did the ANOVA test, and we found that there is no difference across 3 groups. Okay. So it is safe to say that there is a very minimal bias or any kinds of imbalance among the participants. But at T2, as you can see, both the VR condition and the video condition exhibited the significantly higher intercultural sensitivity compared to the control group. And the most intriguing part is actually at T3. As you can see, the VR group retained the effects quite well, okay? But for the video group, we can see a very huge relapse, basically, okay? So, so this basically answers the question, why VR, okay? It seems like VR has the best effects, retained effects, okay, of the change in the participants' intercultural sensitivity. For question number 5, we are going to use the hierarchical multilinear regression, as I mentioned before, to do the linear regression. We have the 2 blocks of independent variables. Block 1 has the participants' age and gender. Block 2 has the IPQ score and empathic concern score. And for the dependent variable, we use the change of ISS score between T1 and T2. So the result is very interesting when we just look for the age and gender, and we found that they did not significantly contribute to the dependent variable. But when we enter IPQ and also empathic concern scores as the independent variable into the model, we found the model is significant, and also 64.07% of the variation in the dependent variable was explained. Okay, and also both of the IPQ score and also the empathic concern score contributed to the model significantly. Okay. So the last one would be some key takeaways. Because of the length of the presentation, I cannot cover everything. So I just give you 3 major key takeaways. So for others, you may refer to the paper. So the first takeaway is that one-time VR exposure could significantly enhance the participants' intercultural sensitivity, and the change could be retained for at least 3 weeks. Okay. The second is actually the answer to research question number 5. Okay. So we found that the change in intercultural sensitivity between the baseline and the right after the VR exposure could be well predicted by the participants' sense of presence during the VR exposure, as well as their emotional empathy. Okay. And the last one, which I haven't covered in our presentation, but this is also a very interesting finding, and you may find more information in the paper. It says that the emotional empathy was also a strong predictor of the change in intercultural sensitivity between the baseline and 3 weeks after the exposure. Okay, so we are talking about the retained effects. But the sense of presence was found to be a weaker predictor. Okay, so we think that maybe VR is very good to bump up people's intercultural sensitivity right after the exposure, but as time goes by, it still relies on the person's trait. Okay, so emotional empathy. Yeah, so that's it for today, and thank you for listening.
Thank you very much, sir. It was a really interesting study. Any question?
Yes, hello, thank you. I'm Mirjam Vosmeer from Amsterdam. Thanks for the very interesting presentation. I was wondering, could you tell us a bit more about how you made the stimuli? Because you told us it was 3 different locations in Hong Kong, but what actually happened in the VR condition and in the video condition? Were people told things, or did they meet someone who was telling them things? What was the content of the test?
Yeah, this This is actually a very important question.
Thank you.
So, but due to the time limit, I cannot show the video. Yeah, but you can find the video with the paper. Basically, for the first, for all these 3 different locations, we embed some information. Okay, so that those information are related to intercultural knowledge. So, for example, it talks about why there are ethnic minorities in Hong Kong, things like that. Okay, so they are all facts. Okay, so for the participants, they need to navigate within the scene. So you can imagine that we have a quite large map of a game, and they have to progress into different rooms to find these treasures. Okay, and after that, they will proceed to the next scenario. So we did the 3 scenarios in total. So for the video group, we basically use the video recording, okay, screen recording of our staff doing these experiencing at a average pace, and we just replay the entire process, yeah, through the video. Yeah, I hope that answers your question. Yeah, but more details can be found in the paper and also a previous publication. Yeah,
okay,
in the IEEE VR. Yeah.
Thank you.
Thank you very much. Any other question? If not, we can thanks Chen for the amazing insights. Thank you very much, Chen.
Okay, thank you.
And I would invite Jae-Yun Shin to talk about her research on the effects of device and spatial layout on social presence during a dynamic remote collaboration task. Reality.
Right. Hello, my name is Jae-Yun Shin, and I'm a postdoctoral researcher at the Augmented Reality Research Center at KAIST. Our paper is titled The Effects of Device and Spatial Layout on Social Presence During a Dynamic Remote Collaboration Task in Mixed Reality, and was co-authored with Boram Yoon, Doo-Young Kim, Hyung-il Kim, and Woon-Tak Oh. So for asymmetric MR remote collaboration, AR and VR HMDs offer the highest level of spatiality by placing the user within a 3D environment. They're especially advantageous for dynamic, space-centric collaboration that involves active movement throughout the shared space, as opposed to static, object-centric collaboration, where movement is bound to, I'm sorry, I'm showing the wrong slide. Yeah, where movement is bound to a limited area, like Horizon workrooms. So in dynamic MR remote collaboration, exploration of the shared space through physical activities enables users to obtain more detailed information on the task and the other user, thereby raising social presence. And these activities are largely conditioned by the representation and configuration of the shared space and its components. So fundamental differences between AR and VR in how they connect the real and virtual may lead to disparate levels of social presence, and discrepancies in the spatial affordance of each user's environment may also contribute to such an imbalance in user experience. To explore this issue, we conducted a user study comparing the effects of 2 different MR devices and spatial layouts on the social presence of users engaged in a remote collaboration task that required active movement within the shared virtual space. So we first looked into prior works that provided hints on the relationships between social presence, mediation, and spatial affordance in MR remote collaboration. Social presence is defined as the degree of salience of the other in the interaction and the consequent salience of interpersonal relationships. And factors of co-presence or spatial presence, which each refer to the interpersonal and environmental aspect, are used to evaluate social presence in various media experiences. While co-presence is the feeling of being with others, spatial presence is the feeling of being there in the mediated environment. So therefore, the mode in which the interactant is mediated and presented to the user is a key factor. Many previous works investigated how factors of social presence are affected in various modes of AR and VR for MR remote collaboration. While some studies found that AR HMDs fared better than projections or VR HMDs, others found that VR HMDs were more beneficial than most AR environments, especially regarding their superior field of view. While they provided the grounds for our study, none of them directly dealt with remote collaboration between AR HMD and VR HMD users involved in a dynamic task. Next, spatial affordance refers to the relationships between the user's physical capacity and features of the environment. Traversability and visibility are dimensions of spatial affordance associated with the degree of freedom and ease of movement and visual perception, respectively. The affordances of a virtual space are linked to spatial presence, which is an aspect of social presence concerning perceived action possibilities for human-environment interaction. So the user's awareness of their physical abilities is determined by the extent to which configurations of the virtual space impose constraints on them. And as to how spatial affordance affects factors of social presence in MR, prior works found that spaces where users can experience higher traversability, more exposure to one's own natural body movements, more interaction, and a sufficiently sized free space with few visual obstacles are more beneficial. But again, none of these works focused on how specific configurations can condition collaboration spaces for AR and VR users performing a dynamic task through HMDs. So for this study, we asked how the mode of mediation and the layout of the shared space affects social presence, spatial presence, and perceived workload during dynamic MR remote collaboration. We also sought to observe how users move, perceive, and interact under the given conditions. And based on the related work, we set up 3 sets of hypotheses with regard to our independent and dependent variables that will be covered in detail in the later part of this presentation. We designed a task that required a pair of users to search for 10 parts of a virtual Mars exploration rover, which were distributed among a total of 20 virtual objects in the space, and assemble them onto a single frame together. The primary rationale was to ensure that the task engaged both users in active and constant movement across the shared space. And the task was symmetric in that the same role was assigned to every participant. We then conducted a 2x2 between subject study with 2 types of devices supporting immersive and dynamic remote collaboration in a shared 3D MR environment, an AR HMD for the host user and a VR HMD for the remote user, and 2 types of shared space layouts in comparing factors of social presence. The size of the shared space for both layouts was fixed at 15.72 square meters, which provided sufficient room in both layouts for virtual objects to be placed apart and the participants to walk freely about them. The peripheral layout afforded higher traversability and lower visual complexity, with all the furniture items touching the walls. On the other hand, the scatter condition provided lower traversability and higher visual complexity by dispersing them throughout the space. The position of furniture items in the scattered layout was determined by 2 principles, which were spatial zoning and functionality, which means that they created sub-areas within the space and were aligned according to pairwise functional relationships. We measured social presence, spatial presence, perceived workload, and task completion time as dependent variables. The network mind measure and the temporal presence inventory were used for multifaceted analysis of social presence and its subfactors. Spatial presence was evaluated through the spatial presence experience scale and perceived workload by the NASA task load index. A total of 48 participants between the ages of 20 to 43 participated, and they had varying degrees of experience with AR or VR HMDs. For the study, we first paired them randomly and walked them through the task with instructions and practice sessions. After completing the task, they answered the questionnaires and gave semi-structured interviews, which took an average of 30 minutes per session. So if we look at the results for social presence and its subfactors, results showed that users wearing a VR HMD felt significantly higher social presence overall, as measured by the TPI, along with co-presence and actor with a medium as subfactors of the Network Minds questionnaire. Regarding attentional allocation, users in the peripheral layout reported significantly higher scores than those in the scattered layout. Turning to spatial presence and its subfactors, self-location and possible actions all of them were significantly higher for users wearing VR HMDs than those that were wearing AR HMDs. And to observe patterns in movement within each condition, we log the position vectors of the HMDs every second and visualize them as accumulated trajectories and heat maps. This revealed that in both layouts, AR users tended to avoid passing through the virtual frame they were required to assemble the Mars rover parts onto, which was placed at the center of the shared space. But in contrast, the remote VR users showed little regard for the virtual frame in moving around the shared space, and they did not hesitate to pass through the virtual frames, regardless of how the space was laid out. And to analyze how the paired users interacted with one another, we visualized the pairs of trajectories for every session and looked for dominant patterns in each layout. We found that in the peripheral layout, most pairs collaborated in intersecting trajectories within a shared spatial boundary and were in closer contact with one another throughout the task. On the contrary, most pairs in the scattered layout kept their distance from one another, moving in isolated trajectories within separate spatial boundaries and engaged in less communication. Also, in-session monitoring logs and video playbacks show that while users in the peripheral layout usually maintain their gaze at eye level, those in the scattered often look downwards in search of the parts. In addition, AR HMD users tended to turn their heads more frequently than VR HMD users, who were more inclined to focus their sight in the direction they were moving. So although we hypothesized that social presence will be higher in AR, we found that interpersonal aspects of social presence were higher for VR HMD users. And we assumed that this is because it was easier for VR users to perceive their partner than the AR users did, owing mainly to the superior FOV of the Quest 2. Also, more effort was required for AR users to interact with their partner as they treated virtual elements as if they were real, which caused additional constraints on their movement. As to why the amount of attention the paired partners paid to one another was higher in the peripheral layout, we refer to how the different layouts induced them to move in contrasting ways. And adding to the fact that they frequently cross paths, those in the peripheral layout said they focused more on their partner because they found the space to be uninteresting. On the other hand, the scattered layout led users to stay confined in smaller sub-areas, and they gazed downward to search for parts rather than to look to their partners. For perceived message understanding and perceived behavioral interdependence, which were sub-factors of social presence, there was no significant difference between all conditions, because voice communication, which was a consistent factor, had a more dominant effect than device and layout in this regard. And while spatial presence was higher for VR HMD users, there was no difference between layouts. This implies that the sense of being there was closely linked to the degree of immersion that users felt, and many VR users expressed that being completely blocked off from reality, as opposed to being visually oriented in reality to some degree, made it easier for them to concentrate on the space that they were in. And VR users also felt they had more agency in moving around the space than AR users did. Our hypotheses on perceived workload were both rejected, as there was no significant difference between both device and layout. As the task was not complicated nor long, what effects device type and spatial layout may have had were offset by the fact that the workload was considerably low to begin with. So based on our analysis, we proposed 3 design implications for shared spaces with regard to how they can foster better social presence among users wearing VR and AR HMDs for dynamic MR remote collaboration. First, fixing large virtual objects on open surfaces should be avoided, as they induce AR and VR users to move differently and result in disparate levels of co-presence. Second, virtual objects should be leveraged to utilize subspaces as shared task areas in complex layouts that separate collaborators and drive attention away from one another. Third, more virtual objects should be provided at eye level for AR users to reduce the effort they have to make in perceiving the shared space. So in conclusion, dynamic In dynamic, immersive AR/VR remote collaboration, the AR environment and complex spatial configurations should be altered through the adaptive placement of virtual objects in order to achieve consistently high levels of social presence for both sides. Thank you for listening, and for more details, please refer to our paper.
Thank you very much. Any question? Oh, yeah.
Well, thanks a lot for your talk. I have some kind of provocative question. The VR obstacle was not really a VR. That means that you do not enforce spatial affordance of your obstacle. If you had implemented such an affordance, do you believe that it would have changed the result?
I'm not sure if I understood correctly, but did you mean that the obstacles, that the objects that created spatial affordance were not real?
Well, if the obstacle is virtual and then you can cross your obstacle, then you do not enforce the spatial affordance of an obstacle somehow.
Right, so the layout we experimented with, the objects that determined the layout were all real in the AR environment, of course, and in virtual reality, they had to be virtual. But when I talked about how AR users perceived virtual elements to be real and VR users didn't, those objects were not part of the makeup of the environment, and they were objects that were included in the task and that they had to interact with. So I think they, in our experiment at least, they weren't really part of the part of what determines spatial affordance. But on the AR side at least, we found that virtual objects can be considered as real, can be considered in the same way as real objects. So in our design implication, we suggest that virtual objects, especially if they are big in size, they should be considered as a factor that can influence spatial affordance and be leveraged as such. I don't know if that answers your question, but yeah.
Partly, we'll discuss that later if you don't mind.
Any other question? No? Okay. Thanks, Jason. So this concludes this session. Thank you very much for attending. Enjoy the banquet.
Thank you everyone for joining us in the various sessions. You may head outside for some light refreshments that will be served shortly, and then the banquet dinner will be happening at 7 p.m. Thank you.